Ja, doet, hè? Ja, en jij? Tot 5? 5 begint mijn laatste. Nee. 5 uur, 5 uur afgelopen. Test, test. Test, test.
I've got HDMI native. It's fine.
Never mind.
Saya.
Oh, no, it's okay.
No, I got it.
He has it.
Right.
He has a superior computer.
Who wants the
Oh, boy.
headset?
My next one will have an
The
HDMI.
headset. Skylar, do you want the headset? Do you want me to keep the headset?
Or you want this mic?
I think this mic. Or I could go for a headset actually, because I'll wall control.
Okay, yeah, that's fine. You're up there for 5 minutes. I can just use this one. No biggie.
So can we have both then?
You keep the check though?
Oh, yeah. Testing, testing. 1, 2, 3. No.
Are you excited for your talk?
Yeah, I'm excited. I'm Skylar, by the way.
I'm Eugenia.
Are you local? Did you
I'm living in the Netherlands for like 6 years, but I'm Iranian.
Oh, opposite.
No, I'm excited. I've been running
What?
like a lot of the university events always, but then all of my work on Julia, all my 2 talks on my actual science work are both today, and so it's exciting to like
To dive into your
instead of
Oh,
rushing
maybe we can't use this. Skylar, can you like switch slides if I like wave my hand or something?
Oh, if I stand up here?
Yeah.
Because you're gonna walk
Because I'm
around.
gonna. Yeah.
Yes, I will just be really dialed in on.
I thought maybe it's like new technology, you know?
Yeah.
Yeah, everyone will be like, ooh, how do we do that? But it's just me. You gotta have a co-speaker.
Natural AI.
Collaboration.
Hello.
Hey, good morning.
Oh, this is on. Is this
Yeah,
on?
don't breathe too loud while I'm talking.
I'll be quiet as a mouse, I swear.
Yeah,
We wait a bit because keynote talk is still kind of going.
Oh, we're gonna start for another 10 minutes. Beautiful, beautiful dirt. I'm going to.
So, what? Same controls, right? Arrow, arrow.
Yeah.
Yeah. Okay. Excellent.
I'll just use the down arrow. Yeah.
Yeah. Okay.
Don't want to give too many sneak peeks.
Yeah.
I'm excited though.
So bad, like on the way here, I had to check the directions one moment. I stepped into a puddle like ankle height.
Fired in socks.
I'm so glad that I brought dry socks.
Dude, that's a genius idea. My sock was too wet.
It's like squelching all
I had
day.
an umbrella, but it didn't go to the.
Yeah. It was a lot of rain. That's okay. I'm just like playing with the clip. I have today is my entire like weather themed episode.
Yeah, it's
For the
really
Earth.
nice.
Thank you for the Earth Science Mini.
I guess I'm big too.
Yeah, you're the jacket.
But your earrings look very cool. Are they handmade?
I think so. I got them at an art fair.
Oh wow.
I was looking for ring ones and they had them.
Oh, fascinating.
Yes, thank you. Yes, this is my now that I do a lot of nuclear science and now I'm moving into fluid dynamics, right? So this is gonna be like my conference fit until I'm done with my PhD. I guess.
Waar je alleen maar heftige wijze wordt.
And where is Raphael? Where is he?
He'll make his way up at some point.
He's not going to talk, so if he doesn't make it, we'll just give him a shout out next time. So hopefully he'll make it. By when we're He hasn't. Have you seen him yet? He didn't-
Yeah, no, we were sitting together downstairs.
Yeah, he'll probably make it, but it's okay if he doesn't.
You saw him. You bumped into me when you were.
Oh yeah, you're right. You're right.
Should I introduce directly at 10:10? I'm not sure how it works. And first time.
For all of us then.
Yeah, I think that. Yeah.
Yeah?
Yeah, I think you should
Okay.
introduce us.
Okay.
Yeah. No
Okay.
worries.
It's all good.
No. Yeah, we're pretty relaxed about this.
Very
Don't worry about it.
Okay.
It's probably good to keep things on.
There you go.
Yeah, there he is. The one walking.
Just give us a wave when you say it.
Anshul, at what time did you actually notice that this talk was moved to Santan? I only noticed this morning. I was like, oh.
Hi guys. It's time to kick off. It's raining, but I'm glad you're all here. And let's start with geometry package developed by its authors. And they're going to give a talk, Anshul, Skylar, and Raphael. Shout out to them. And let's start.
Okay, can you guys hear me? Is the mic on? Yep. All right, good morning, everyone. So thank you for coming so early this morning on our last day of JuliaCon. So today we're going to tell you about a package we've been working on called Geometry Ops, which does geospatial operations in Julia. And so your first question with that might be, what are geospatial operations, especially if you're not super in the geometry ecosystem yet? And these are operations involving geospatial objects. That's not much more descriptive, but basically that means things like polygons, lines, points, some of these shapes that we have up on the slide. And the operations can mean a lot of things. Things where we take in geospatial objects and output values like area or centroid. Things where we take multiple geospatial objects together and output a new one, like union, difference, or intersection, or where we change a single geospatial object, such as simplifying it, or finding something called its convex hull. So these are really important for a huge range of problems, but how do we do them in Julia? What does the ecosystem look like? And honestly, it's a very varied ecosystem. But there's sort of two camps of packages just due to somewhat the newness of Julia, and that's sort of wrappers of big existing packages in other languages, for example, C, C++, or in some cases, smaller packages that are implementing 1 or 2 or 3 features as users need them. And so this is a small subset of the packages in the Julia geometry ecosystem. That's our super cool logo. And these fall into some of the camps that I was talking about either being non-native or pretty limited. And actually, some of the blue ones I've put up here haven't had commits for like minimum of 2 years. So it really is on a per user basis in a lot of cases. And so what do we really want? Well, we want to build on the strength of a lot of these packages that people have been building, really use the manpower of people in the Julia community who are already working on these things, and build one package with enough methods and interoperability to build a real community of users and developers for the good of the ecosystem. And so we're really hoping that that will be Geometry Ops, and that it'll be a really flexible package that'll perform a really large range of these geospatial operations that I was talking about earlier. And this is sort of our group of people who have worked on the package so far, and we're really putting a lot of time and effort into building it as quickly as possible. And so I'm going to start off by telling you why should you use Geometry Ops. And like I mentioned, this is really actively developed. We're pushing basically weekly at this point. It's fully native. And we're really focusing on flexibility and modularity to make it easy to add new algorithms, new functionality, whatever you might need, which Anshul is going to build on. And we're trying to avoid things that come with working with things like C, or things that aren't really built in a really Julian way, like seg faults, type instability, and really rigid algorithm choices. But I won't say it's all roses. Why should you not use geometry ops? It's brand new, right? There are bugs. The geometry ecosystem's still building cohesion. What is an empty geometry? Some really interesting questions we'd love to talk about. But I'm going to pitch that this is actually why you should help us develop geometry ops. We need some polish to reach our full potential. So help us grow from this really awkward young child package, into this really strong unifying package we want to become. And I'm going to let Anshul give you some of the details.
Right, so is this working?
Yes.
Perfect, okay. So let's talk about the plan. So the plan was, we need speed, right? We've got to go fast. This is Julia. And the idea was, all of these industry standard packages have a lot of overhead. They're built for gigantic geometries, millions of points, and they've got a lot of caching, a lot of overhead. So we said, okay, let's re-implement this stuff from the papers. We'll get the new algorithms, we'll minimize the overhead. And a lot of our needs were also for these really small polygons, right, in simulation and so on. And so that actually helped us quite a bit. You can also group similar computations together. So when you're computing the centroid, you're doing a pass over the polygon anyway. So you may as well compute the area. It's not that difficult. You have to do it anyway. So we can return that as well. We provide generic algorithms and let users choose between them. So for example, let's say you're simplifying a geometry, right? You've got a geometry with a lot of points. You want to decrease the number of points, but still keep the general shape. There are multiple algorithms which do this. In a lot of packages, you have to find the function name. There may be different arguments and so on and so forth. In geometry ops, you just pass an algorithm struct. It's like diffie-q. It's really simple. So the idea is to also sort of lower the barrier to entry, right? Because if you're pushing an algorithm to one of these established libraries, you have to make sure it's better than anything else. With this ability to choose, you don't need to do that. It's an algorithm. It works for your use case. It works for this particular type of thing you want to do. Great, push it. People can use it. So to create the solution, we need flexible frameworks to create these algorithms. And we've created this function called apply. So the idea is that geometries are sort of like a tree structure, right? You've got on the top, let's say, a multi-polygon, which is a collection of polygons. Polygon is a connection of line strings or linear rings, which is a collection of points. And so this apply function basically walks through that tree for you and decomposes to whatever level on that tree you want to give it. So for example, you can go for points, you could go for line strings if you wanted, or linear rings, or polygons, and so on. And the beauty of this is that geom can be anything. It can be a geometry, vector of geometries, a table, some other data structure. As long it's extremely flexible. And in this case, we're just flipping the x and y coordinates, right? And this is all done generically via geointerface.jl. So to give you an example of this sort of algorithm choice that we're talking about, let's talk about geometry segmentization. So this is just a rectangle, sort of rotated around, right? And the blue rectangle, which is kind of overshadowed by the orange one, is what you would see if you just plotted that rectangle. And it's also what you see if you linearly interpolate along the line. So we initially defined the rectangle as 0.1, 0.2, 0.3, 0.4. Right? So just these 4 points, which are sort of the minimum required definition. But you can use the segmentize function to interpolate along the lines. And if you just say segmentize, it'll give you a linear segmentization, right? Linear interpolation. But if you pass this geodesic segment struct as the algorithm, it actually calls into a C library which does computations on the ellipsoid. Is the mic working? Yes? Okay, perfect. It does computations on the ellipsoid, and you'll notice that in longitude, latitude space, this polygon is curved because it's on the ellipsoid, right? It's pretty high on the ellipsoid. I think this is somewhere in the North Sea or something like this, so you can sort of get a perspective of where this is. Next slide. Yeah. So as I said, give users a choice. You can choose lots of pre-processing, like what Geos does, for example. And you can actually, there is an algorithm called Geos, which lets you call into the industry standard Geos library, which is in C. You can choose no pre-processing if you want. And as I said, this lowers the barrier of entry for new algorithms. Even if it doesn't work for everything, if it works for some things, and it's not so optimal for other things, you can still add it. Now, benchmarks, of course. We're in Julia. We've got to have the benchmarks. So this is an example of that segmentized thing I was showing you. The blue line here is libgeos. That's a C library wrapper in Julia. The green line doing the exact same thing as libgeos, but in Julia. And so we get rid of a lot of that overhead that comes from A, the implementation of the C library, but B, also calling into C. And then the beauty of the choice is we've got this super fast algorithm. If you want exactness, you can call this orange line, which is geodesic. It takes a longer time, but it's sort of more exact and so on, right? So now again, talking about polygon operations, here's where we don't quite beat C, which is orange here, and blue is geometry ops. This is computing area on just a circle. But you can see that we get rid of some of the overhead for really small polygons. As your computation becomes larger, they sort of equalize. And here, this is fun. So again, really small polygons. What's going on here, the blue is geometry ops, the orange is libgeos. And sorry, how much time do I have? 2 minutes. Oh boy. Blue is geometry ops, red is orange is libgeos. And you can see that for small polygons on the order of 10 to the 1 points to about 100 points or so, you don't really need the caching that Geos does. After that, you can see that Geos' caching really improves performance. And the beauty is, of course, you can choose either, depending on your use case. So I think we'll forward through this for the sake of time. And this is actually a nice benchmark. So there's in the geospatial sort of ecosystem, there's a cross-language benchmark repo called Vector Benchmark. And over here, I've given each package a logo according to the logo of the language it's in. So you can see the little R's, the little snake for Python, right? And of course, Julia. And geometry ops is in green. All the other packages are different colors. Is this pretty visible, or should I sort of explain what's going on?
Just mention it's a log scale.
Yes, it is in log scale. The median time per operation, it is in log scale. That's a good point. And you can see that geometry ops is actually pretty fast. A lot of this is just decreasing overhead. A lot of this is the fact that Julia is fast, and we have all this nice type stability stuff. Even reading and writing, for example, right? Load and write, that's just done through GDAL for now, which is the Geospatial Data Abstraction Library. That's what everyone uses. But because Julia's C calls are so fast, Julia is actually faster than, for example, the Terra library in R, which is also using the same underlying C library. So I think that's pretty cool.
Yeah.
And I think we'll have to cut it there, but if you are interested in developing on this library, we're trying to push, we're getting to be some of the fastest in the ecosystem, and we would love any help if you're interested.
All right.
Thank you.
Thank you so much for the talk. Yeah, the questions during lunch. I would like to welcome our second speaker for today, Ole. And we will explore cities with Julia,
really
with
went
Ole.
over that.
And
I think there was some changes in schedule. The second speaker, I think, is me.
No, all is on the schedule.
yeah, I think it's Ole.
It's definitely
I hope so. Sorry for the time. But,
No worries. I will use this one.
yes, but it's function.
Yeah, I can use this mic. That's fine.
All right.
Oh, perfect.
Let's welcome Ole.
Thank you. Yeah, I would like to present you today my newest side projects of like tens of side projects that I have. And it's a new way to explore a city. So it's called everysinglestreet.jl. And the inspiration for this project was basically sometimes I just walk around the city, but when I walk to work, I always like use the same streets every time. I have my favorite parks, my favorite restaurants, and just always don't really explore the city, just walking the same rounds. And I wanted to change this, so I wanted to stimulate my brain a little bit more. I wanted to see something new, and sometimes it's best to just go into it, go into the extreme, and why not walk every single street of your city, even though it's quite a big one. So the first question of, like, is there already software available? Not too important for me, to be honest, because I just wanted to build my own anyway. But let's try what already exists. Then what is a walkable street. Like, I don't want to walk every single path on every park. I don't think I will ever finish this project. Then some problems that arise is it's easy to just track your GPS data when you walk, but it's not the easiest to map it to the actual street network. Then the last 2 points are basically interleaved a little bit. Like, I want to keep motivated because I know I will take a couple of years for this. So I want to track my progress in different ways. So the websites that already exist are StreetFerret and citystrides.com. I checked them out both. I feel free to use them if you don't want to program, if you are not a Julia nerd. I don't know where they are, but yeah, those exist. There was some functionality that I was missing for some, so I built my own. I'm really glad that OpenStreetMap exists, otherwise I think I would not build my own. With lightosm.jl, I can use it in Julia. I use Strava to just keep track of my GPS data, and oxygen.jl for like API stuff. Then there was no map matching algorithm yet implemented in Julia, at least I couldn't find one. So I built my own. Then I use an app because I didn't want to develop an app myself, but it's quite flexible. I will show you some stuff later. And to keep me motivated, basically, a statistics breakdown of it's not that nice if you walk and you're like, oh, you finished 0.05%. So maybe break it down into districts or stuff like that. Let's start with some interesting tasks that I had to fix, to build. The first one, and basically the most important one, is map matching. So you see here, you have the actual GPS track, and on the right side, you basically have it mapped to the street network. So you get basically some candidate points. Like, the easiest approach would be to just map it to the closest street, but that sometimes fails. So especially when streets are quite close together, and GPS in the city is also not always the best. So you have to do some probability stuff with hidden Markov models. Then another interesting task is basically like you want to have a visualization of it. You want to use it on your phone. So you need a tile server that when you zoom in, you see the streets that you are interested in. This is not built in Julia. At some point I might try, but so far there is existing stuff out there which works. Then another interesting thing was to do like full automation of everything. So like Strava, you can connect to the API. So basically, I receive a new walk from Strava. I do map matching on a small server. Then I do the tile generation and push statistics back. So basically, what you see there, I don't want to go too far away from the microphone, but you see that this is my walk where I finished 20% of my city after 1 year. You have some statistics breakdown for the districts. And to the full right, you basically see a stripped down version of the map. And in green, you see what I already walked. Then some upcoming tasks. I want to maybe do some routing algorithms, but that's quite hard because you don't really sometimes know what actually is your goal. Like, do you want to walk from here to there? Do you just want to spend 5 hours in this district for a day? Stuff like that. Then something that I still have to figure out is how to, for this, like this is quite close by the way, so I use it also for Eindhoven now. This Williamstraat is like basically a 2-lane with like a pedestrian island in the middle, and I don't want to really walk both of them. Then I want to keep track of maybe changes in OpenStreetMap, and maybe in the long run also create a website for non-Julia or Julia users. Feel free to use it, maybe in Genie. Then some short statistics so far. Hamburg, the city where I walk and live, has over 4,000 kilometers of walkable streets. So far have 28% of it reached, and after the first year, 20%. Some links. So this is the project. This is my blog where you can read more about the projects. For map matching, I have a blog post, for example, and some other links. Thank you, and happy walking, running, cycling, whatever you want to choose.
Thank you so much. I think we have time for one question. So does anybody has a question? All right.
Thanks, Ole, for this cool project. I was wondering, the typical formulation of this problem of walking every street is known as the postman problem. In your case, how would you modify it to have certain goals like leisurely walks or visit or whatever? Like, what would be your first tweaks to this standard problem?
So I think the biggest problem with like the standard formulation would be that I don't want to walk this every time, which is probably the best choice, but it's not really nice to just, okay, I want to go in that direction, then I go back, then I go there, then I go back. So maybe I want to have like more scenic rounds of different, like going to the same district like 20 times instead of finishing it up in one. But I think that is quite specific for this type of task. So.
Hi, it's me again. Sorry, we're on a tight schedule, and we're gonna have our third talk for today. We're gonna talk about bestie-template.gl. You all might wonder what it is. Well, let Abel speak and tell us more what it is.
Thank you. Yes, thank you. Thanks a lot for coming for this session. There are many great things happening today, so it's nice to have so many people here. It's my first JuliaCon, so the global one at least, so I'm excited to share this cool project that we're working on. And yes, of course, if you're wondering, it is a jingle. It's bestie, your best practices, friend. Work in progress. So if you do have to leave early, I want to just give you the main takeaways for this package. It is a new template, as the name implies. It's focused on best practices, so we are trying to aggregate many best practices and put them into a package. It has a recommended and a minimum way of using it. So we aggregate the best practices and recommend that you use them, but you have a way of using just like the minimum amount of cool stuff. It's already more than the bare minimum, so see more for more information. And the main difference between this template and other Julia templates is that you can apply to existing packages. So you can use this in your project right now. It's not for new projects. And you can update your package with new versions of the template. So you keep track of the best practices being implemented. It is an evolving project, so we just kick-started it, put some stuff in it. If you want to like give some opinions on what should be there or not, or if you saw some error, please come be part of it. It is looking for new contributors, so please join. And I'll be here tomorrow for the hackathon, helping you set it up if you want, and hopefully gathering feedback from you. Okay, so I want to talk a bit about myself, because I like me. So I was a professor in Brazil in 2014 when I started Julia. So this is more focused on the Julia side of my experience. And I was leaving C++ and MATLAB, so that's why I chose Julia. In 2015, we started the Julia Smooth Optimizers organization. That was my research for many years, and that eventually became, I think, 50 plus packages. And so I felt the pains of managing many packages, especially when you have to update things that are really old. So I got some experience there. I just wanted to point out that I am also the creator of Geo, and probably gonna have to be deprecated now that Julia Up will be the main way to install Julia. And I do have a YouTube, so please like and subscribe. I'm looking at the camera. And so my life changed a lot when I became a research software engineer here in the Netherlands, at the Netherlands eScience Center. So I changed jobs, but I still wanted to work with Julia. It took a while to find the Julia project. And this Julia project came last year, which is the Tulipa Energy, or GitHub name for it. Yes, thank you. And Tulipa Energy has a special place here because it is one of the main reasons that we have this template. A bit about the Netherlands Science Center, also great motivation for this template. We have about 60 research software engineers. We are a not-for-profit institute. We essentially work with researchers from the whole Netherlands. They apply to work with us so they can get some kind of funding. So it's in-kind support. So they ask for help with their projects, and we have someone or a few people assigned to work with them. If you are researching in the Netherlands, please look at our website. You can apply. And our main goal is to empower research, so that has many ways of happening. So we have various projects. We work with various technologies. As I said before, it took a while to use Julia. We use C++ and Python a lot. But whatever you use in your project, please come talk to us. And our involvement simplified is to make things faster. That can be scaling or just finding out what you did wrong. Improving sustainability, which is a major point for this talk in particular. And sometimes we create new stuff or help you extend the stuff that you're doing. And at the Netherlands Science Center, we care a lot about the quality of your code. So we work with research software, but many of the things that we care about also apply to general software, although I think that for JuliaCon, research software is a big part of it, so it's nice to be here. And for us, this quality, it goes hand in hand with the sustainability of your code. So when we think about research software and sustainability, we are worried about the software working a few years ahead. So normally you have a PhD, you do some stuff, and then you're going to do something else, maybe make money, and the code is left behind. So we want to help you during your PhD to make sure that the code will survive. These are a few of the things that we do at the Science Center related to software sustainability. And one of the projects that we started last year was the Tulipa project. It's an energy system optimization. And so they contacted us and they said, well, we are looking to make this new model and we want it to be open, maintainable. So we want to write a good code from the start because it's going to be used by many years. And long after the Science Center leaves the project, we want to make sure that people will know about it. So if you want to know more about Tulipa, we had a talk yesterday by Lauren, so you can see the recording. But the main idea is that we started the project thinking about the best practices. So we aggregated a few Julia best practices and a few non-Julia best practices, put them into the Tulipa repo, started doing our project, documented our process. How do we do branching? How do we use Git for stuff? And so eventually when we started creating other projects in the Tulipa Energy organization, we realized, well, we might as well create a template for this. And so that's the best template. Okay, so starting the actual talk about the best template. Julia is a great language for best practices. It already enforces and recommends many things. So if you try to register your package, you'll see that there are many requirements, and those are great. That's like a great way to start, like semantic versioning, and this like a recommendation for you to have documentation. And if you start your package new by the recommended way, which is using package templates, you have many good defaults already. Like you can start with a CI, for instance, which in many cases for research software is like, what is CI? Right, so it's pretty cool, and the community is very active, so there are always many things popping up. However, we should expect more best practices First, because new ideas keep popping up. So we had some talks here. I do believe there are some talks going on around the morning about new best practices as well, new tooling that we want to adopt. And also, when the popularity of Julia increases, the number of tools will also increase, especially when people realize that they can make money by supporting Julia in some of these other code quality tools, services. And of course, when the adoption increases, you also expect some quality, especially from industry. We had a conversation yesterday about this. So you want to make sure that the code is secure, it doesn't have too many code smells, that kind of thing, right? So we should expect the tooling in Julia and the best practices to keep changing, to keep evolving. And so that's where Besti comes in. We are aggregating these best practices. And since it can be applied to existing packages and reapplied, right, we are kind of solving this problem, which is if you use the template and the tooling changes, you can just get an update, and now you have the most up-to-date tooling. Okay? So from simple things like the tagbot versions changed, update. From, okay, now we're going to use Jet in the CI, update. Okay? Like I mentioned before, we are an evolving template, so there are many things happening. There are many issues. I think I have 50 open issues. And we are not the authority. So it's important to say that we are really, really, really interested in best practices at the Netherlands Design Center, but we are not saying that we have the power to say what are the best practices, but we do have opinions on that, and that's the template. Okay, so I'm going to compare a bit with the package templates, just a little bit. So I'm going to tell what is a project generator tool. So first, you have this tool, a project generator. It's going to send questions to the user. The user will answer these questions. It might be stored somewhere or not. And the project generator takes those questions, put them into the template, and create a package for you. Okay, that's the basics of project generation. Package templates is the project generator and the template. It uses Mustache internally for how it handles placeholder variables and other things. But the idea is that the package template is responsible to sending you the questions and then getting those answers and then putting it into the template and give you the package. Disclaimer, I don't know much about the package template, so you can correct me on this later, but that's from what I understood. So what we are doing at the Besti template is we are not worried about the project generator itself. So we are using Copier, which is an external tool. It's a Python tool. We do have some wrapper around the questions. So because it's a Julia project and we know what a Julia project has or needs, we kind of do some stepping in to say, well, you have a project toml, so let me get a few things already for you, and then keep on. Right? Copier does the thing. We focus mostly on the template itself, so the Besti part, and Copier uses Ginger, so that's also a small difference. Usually you don't have to care about these details, but the most important part is that we are the template and a very thin wrapper, so it's easy Julia code and easy to get inserted into, like to join the project and just look at the template folder and do something. Using Besti template is really easy. So this is an animated GIF of the process. We're not going to go to the GIF, but it's like a few questions, and then you have a project. Just to show you the questions that you have to answer. So you have about 6 questions here. The project name is kind of guessed, UUID, and then some things that I'm not guessing but could be guessed. For some reason, I asked for the indentation length early. I don't want to talk about that now, but also opinions welcome. And then the most important part, I asked, how do you want to handle the optional questions? So what we say is the recommended way, which is using our defaults. So we add a bunch of stuff. Or you can say nothing, I want the minimum, so answer no to everything, right? You also have the option of being really precise and saying, I want this and not that. You can do that programmatically as well, or it's just answering a bunch of other questions. it is a bit more verbose because there are many options, but that's the main idea. So what is inside BASTI template? For version 0.8, which was released Monday. So we have these example repos if you want to actually check them out, the BASTI minimum and BASTI recommended. So I'm going to go over essentially what's inside BASTI minimum here. So first you have the basic Julia stuff, right? So you should know all of this. Except that we also have the answer. So how does copier works? Keeps the answers, and that's it. So it just knows what you answered so you can update later. All the rest is pretty basic. Source has one file, test has run tests. Then you have formatting stuff. So in the minimum, we already put the formatting there. So Julia formatter, non-intrusive file, picked up by VS Code. You want to have that. And you have editor config, which is also a really non-intrusive file picked up by many editors. It has very, very little information, but if you send this to someone that doesn't have any editor, they open this on the server with VI, editor config is on the VI on the server, so it just works. Okay? At least NeoVim, I guess Vim as well. The other thing that we add there by default is citation.cff. Since most of our projects are research software, citation is really important to us. We want you to cite the software, not just the paper associated. So we have the citation file format that we are involved. And so citation.cff is a bit of a biased addition. You have the minimum information, and you can fill this up later. There is a link for the CFF init. So this is what happens if you add a citation.cff. GitHub picks it up, and then you can just click cite this repository, click on bibtag, and then you have a bibtag citation that you then just copy-paste. And as I mentioned, CFF init is a way to create your citation CFF. This is free advertising. Oh, of course, you also have the workflows. So the workflows are not an option. It's part of the minimum. You want to have these things there. It's mostly what you already know. So the main difference is that we have a link here that I'll say a bit more later. And we have this reusable test because we separate your test from the test on the pull requests. So we made this choice to have tests on pull request to be on a smaller matrix because testing on Windows 1.6 took twice as long as testing on Ubuntu latest. So let's test the PRs just on the really fast stuff. If it breaks, we fix it, but otherwise we just test the quick stuff. And of course, you should know compat helper, you should know about the docs, and you should know about tagbot. So talking about the docs, we have the docs. The docs are there. One big difference, or maybe small, we chose to have numbered files, not number file, numbered files, except for the index for building reasons. So when you add your new file, you say 10-intro 20-tutorial. This is picked up automatically, so the ordering of the pages is there. You don't have to touch make.jl, okay? So it's a bit easier to get started with the documentation. And we have this lychee.toml file, which is used in the link.yaml workflow that I mentioned before. It's a link checker. So if somewhere in your markdown files you put a link and it's broken, you're going to have a message in your pull request. So this is how the build looks like. You can run this locally. And finally, for the minimum options, you also have a pull request template. It's not really intrusive. I mean, when you create the pull request, you're going to have some markdown things already filled up. So, and if you just ignore that and press create, this is what's going to pop up, which is the list of related issues, and you fill nothing, closes something, and a checklist. We believe the checklist, just having this checklist helps sustainability a bit, because the person creating the pull request will, okay, yeah, I forgot that docs should be there. Okay, so that's like a really non-intrusive file to have. Okay, then finally you have the recommended things. So this is inside BASTI recommender if you want to check it out. The These are a bit more intrusive, starting with what I think will change a lot the way you develop, which is pre-commit. Pre-commit has been adopted by a few packages. A few people have pre-commit. So for instance, you can see Julia Formatter is already here. It was maintained when we started pre-commit. And what pre-commit does is when you commit, right before that, it will run a bunch of checks, right? So if you have many tools, it will run all of these linter tools. It can run formatters. It can run other cool stuff. Like for instance, I want to check that I'm not committing to branch main. So if you want to avoid people from committing to main, start here, right? Of course, they have to install pre-commit, but that's something else. So talking about people ignoring pre-commit, we have a linked .yaml workflow. And if you choose to use the recommended things, the linter actually runs the pre-commit. So if people ignore the pre-commit and they make a mistake, online you will see in the pull request, it's failing because somebody forgot to do the thing, okay? There is also a pre-commit update to update the versions of pre-commit. Maybe this will change with renovate. We'll see that later eventually. We also have on our recommended options the contribution docs. So one thing that we find very important is how to get people started. And we separate this in two parts. One is the contributing.md. This is normally in the root of many GitHub projects. But since Julia has a nice docs, let's just put it in the docs. So this is like, hey, you want to get involved? This is how you open an issue. Go here. No code. Just do these things. And then you have the developer documentation. Sometimes we call it readme.dev. The developer documentation has more critical information for you to start the project. For instance, this is how you install the dependencies. This is how you branch. This is how we name things. Depends on what you want to extend. But the basic already has a lot of stuff. The other thing that we are recommended is on the recognition of contributors. So it's pretty hard to recognize contributions. What we normally have is the contribution list from GitHub. This gives it a more structured approach. So all contributors is an older project already. And what you do is install all contributors, the bot. And you can say, when in a pull request or an issue, at all contributors, please add this person for this thing. So for code, review, ideas, whatever. And it will create a pull request that will add the person to the README and the docs. So now in the README of your project and in the documentation main page, you have the contributors, which is pretty nice. It's a pretty nice way, not really intrusive, to add some recognition to the contributors, right? So one other thing that we have are the issue templates. These we feel are a bit more intrusive, so that's why it's recommended, not in the minimum. And the issue templates are essentially YAML files. And when somebody tries to create an issue, it's going to give a list based on that YAML file for the person to choose. And that essentially becomes a form on GitHub. And you can say, this is required. And it makes your life a lot easier, especially for bug reports. You can ask for a reproduction, like a minimum working example of the bug. And it does help your project be more sustainable. Lastly, we also have a code of conduct. So which shows the code of conduct from Contributor Covenant. Still open to discussion whether we want to choose another one or not. This is a nice one to have. We had it in other projects. So opinions are welcome. So what is next for Basti? Well, tomorrow, which is really next, you can join me, maybe hacking actually one of the issues, or you can just try it out, create a new repo, apply to your repo, give us feedback. It is evolving, so we are looking for more best practices. If you just say, hey, you're missing this new issue, that's a contribution. Please do that. But if you really want to I want to go deep into why do we need this, let's create a discussion, let's code. We have a wish list, so in the future, we hope to have more tooling. For instance, One tooling that I was looking for was a docstring linter, and I could not find anything, although there were docstrings packages, no docstring linting. So it's still a bit of a mess how we structure our docstrings because, well, I'm going to have to check manually every pull request. So it would be ideal to have a linter for that as well, right? There is also some tentative auto update. It's pretty hard to update these automatically because when you update, there might be conflicts. So what do you do with conflicts? Help is welcome. And finally, there is a discussion about maybe we should have some non-tooling best practices. So there's a lot of effort right now about how do you do Julia properly, right? So we have the modern workflow that was mentioned in the opening ceremony, the State of Julia. There are the Julia Kitchen in this afternoon, I think at 2, that has a bunch of Julia information. And I guess there are many more other initiatives going on. So maybe we join one of these and contribute to process as well. And that's it for me. I have stickers. If you want some stickers, please have some stickers. Thank you.
Thank you so much, Abel, for introducing to us your bestie. And now maybe somebody has questions. Of course.
Thank you. It sounds super cool, especially the thing about that it can be updated, which PKG template doesn't do. Could you say a little bit more about this update process? How do you avoid sort of overwriting stuff that shouldn't be updated?
Great question. Okay, this is working great. So what we do is essentially we use Copier for that. So the way that we handle things is we are lazy, so we mostly use existing things. Copier is responsible for the auto update, and what Copier does is they use Git to check the last version that you have installed, the new version, and that patch is applied. We chose to not do any kind of commit with that. So essentially what you're going to have after an update is a modification of your Git workflow. So it's like you're going to review everything yourself and decide what you want or not. Normally, README has some like overwriting that you don't want to keep, at least for the few first times. But otherwise, it's things that you want to overwrite. Thank you. Thanks for the question.
Yes, great tool. Thanks for the talk. I was wondering how customizable is the template? So, for example, if I'm working in an organization and not all of these questions on the template might apply, so how easy is it for me to customize that and to come up with my own template?
Great question as well. So there are I would say two parts of that. One is, let's say you want some of the existing things that are questions. So there is one of the fields on the generation or application of the template, which is the data. So the answers for what you want. So maybe you are in a company and say, okay, these are the questions that we want on the BASIC template. So always use this. So you import BASIC template, you import BASIC template internal, and then you say data equals BASIC template internal.data, something like that, right? So you always have the same answers. The second question would be, how can we add more? So that's a harder question. One thing that we are considering is we have some of these things, if they are public, right? If they are public, we have some of these things, and they are not part of the minimum or the recommended. So for instance, right now we have a Cirrus file for FreeBSD testing. Julia's multi-optimizers uses that, so let's have that there. But it's not in nowhere's repo unless you explicitly add Cirrus CI. So that's an option. If it's not public and you can't add to the template, I don't have an answer. So we can discuss that.
All right, I think we have room for 1 or 2 questions.
Yeah, thanks, Abel. As you know, I maintain PKG templates, and I also write the modern workflows blog. So in light of that, I think this is the best idea. What you're proposing, it makes so much more sense because it's adaptive. One thing that I wanted to ask is, how do you test it? The best way we came up with in PKG templates is compare the text files, and I'm not completely satisfied with that because we generate the text file ourselves, basically. So It's kind of a fake test. How do you do it?
So for now we have two tests. One very simple, which is the actual let's test generated template. It's just see what's generated, run the docs, does it build, and run the test, does it passes. And then the other test is we are testing that it's consistent with the copier itself. So if you ignore completely the package and just take the URL and say copier directly from your Python, you will have a template. So we are just testing consistency between what copier generates and what best generates. So we are thinking about should we have like best minimum, and then we always run the template and check every file. So it will be great to have your opinion on whether that will be a great idea or not. I mean, otherwise we don't have many more tests. So.
All right, I think that's it for question. Thank you so much again. And more questions during lunch, I guess.
Is that a break
No.
now?
All right, we're just on time for our next talk. We're gonna have Frederick explaining to us about sampled data systems and the new tools that we can use for modeling and simulation. Let's welcome Frederick.
Thank you. Thank you. Let's see. Okay, we're on time. So my name is Fredrik. I go by these avatars on the online platforms. And today we'll talk about discrete time modeling in Modeling Toolkit and whatever that means. All right, so on the screen here I have two groups of emojis. I will try to point. On the left-hand side we have some things that occur in nature. We have a planet, we have a car, we have a funny monkey and so on. And on the right-hand side we have devices mostly. We have a computer, a phone. For the purpose of this talk, these two are the same. We have some currency here. This represents data that we have recorded at certain time points. Okay, so I was limited to whatever is representable as an emoji. We have a clock. There is only an analog clock emoji, but this clock, what is important is that it ticks. And it doesn't obviously tick all the time. It ticks at certain points in time. We also have here is an integral sign, and here is a summation sign, and they will become important. So all of the emojis on the left-hand side have something in common, which is different from what these guys here on the right-hand side have in common. Any takes on what they have in common on the left? Chris, what do they have in common? Their state exists on a continuous timeline. Okay, so from the time this monkey was born, no matter what time point you pick, the monkey has a particular state. All right, but the data here we have recorded for this currency. We recorded that at a particular time and at another particular time, but in between we don't have access to that data. It's not available. All right, so these kind of represent something that happens on a discrete time variable, whereas these are continuous in time. All right, so to illustrate that a bit more, we have a graph. The guys on the left, the continuous time characters, they draw kind of trace out smooth graphs as a function of time. Whereas the guys on the right here, they are defined at particular points in time, and in between they are just not defined. There is no such things as talking about their state at time points in between. All right. And when we model these systems on the left-hand side, the state of the monkey and the basketball player and so on, we might use differential equations. So the derivative of their state, the state here is called x. I'm from control theory background, so we use x for state. It's a function of the current state and some input u and maybe parameters in time. Whereas here on the right-hand side, we also model change in some sense. But we model what is the state at the next time point as a function of the state at the current time point. So k here is kind of a sequence index. So x of k is the x at the current time point, whereas xk plus 1 is then the next state. All right, but what happens then if I draw this diagram? So I have one guy from the left. It's a car. It has a continuous state, position and velocity and so on, angle of the wheels. And then we have a computer, which has a discrete time variable. They don't even have the same time variable. How can we put them in the same diagram? Does that even make sense? And this diagram maybe does not make sense, but we will try to insert some things that make it make sense. So now the diagram has become more complex. We have some graphs also. And what has happened in the diagram is that we have inserted two, I call them operators. So there is a sample operator. So sample means to take a measurement, and there is also a little clock associated with that. So we take a measurement when the clock ticks. All right, and the other operator is hold. So that's a way to interpolate. So we define something at a particular point in time, and then we hold that constant until the clock ticks again. Right, so we will kind of break that down and relate it to the graphs. So if we consider the sample operator, it's a transition from the continuous time domain to a discrete time domain. And I say a discrete time domain because there might be multiple different discrete time domains. Because we might have multiple different clocks in a system and in a model. So on the left-hand side, maybe I will try to point with a pointer instead. Let's say we have the car. It has an acceleration profile. So this is my mother driving. She pressed the gas and the brake and the gas and the brake, and your head goes like this. But it does so continuously. All right. And then we insert a sample operator. So we take a measurement of what is going on here, maybe using an accelerometer. And we do that when the clock ticks. And the clock here maybe belongs in a computer or some electronic device. And then we get a sample, a measurement, and that is represented here in orange in this curve. But then it takes a while until the clock ticks again, and we have no clue in the discrete time world what happens in between there. We are certainly not having a constant acceleration in between there. So we just don't know is the fundamental aspect. But the continuous time world, of course, still continues to evolve in between there. And when the clock ticks, the computer performs some computation. It's in the nature of a computer. It wants to do that. And it comes out with some output. So this may be a controller for a cruise controller in the car, something like that. And that output is then defined at the clock tick. But we might want to make that available to the continuous time world so it can control the throttle or the brake or what have you, right? And what we do then is we insert a hold operator. So we say that take the last available defined value and hold that constant until something else happens. There are other ways you might interpolate from discrete time to continuous time, but for now we will just stick to the zero order hold. Zero order hold meaning that you hold it constant. It's a zero order polynomial. All right, so how do we model such a system in Modeling Toolkit? We have introduced this little convenience object called a shift index. All right, so here I call the shift index k. I create such an index. You can use this as an argument to your variables. So typically, maybe in Modeling Toolkit, we define variables using this syntax x of t, indicating that x is a function of time. All right. Discrete time variables are also defined in the same way. But when we index a variable using the shift index, we have now told Modeling Toolkit that I am now talking about what happens when the clock ticks. Okay? So in the equation, I of k is now related to I of k minus 1. So the current value of I is related to a past value of I plus the current value of some other variable e here. And then I use the sample and the hold operators to transition between time domains. So on the right-hand side here, I have a model. I hope it's large enough for you to see there. It's a regular modeling toolkit model using the macro syntax. I start by creating this little shift index here, and then say at mtk model, my discrete model. I define some variables. It looks exactly the same as it does for continuous time systems. I have some parameters, and then I have equations. And I have split the equations into 2 groups here. But my splitting into groups is only using comments, so Modeling Toolkit doesn't actually care about that splitting. I have 3 equations related to a car. Okay, it's a very simple first-order car. And we see the first equation says that u, there is a variable called u, is equal to hold of ud. All right, so I haven't said what is continuous and what is discrete here. But Modeling Toolkit is smart, and there is some information in this hold operator. All right, so Modeling Toolkit knows that you can only hold discrete time variables. So therefore, ud must be discrete time. And the result of holding a discrete time variable is a continuous time variable. So u must be continuous time. So even though I haven't said what is continuous and discrete, Modeling Toolkit will figure it out based on how you use it. And if you try to use a variable so it's ambiguous, whether it's continuous or discrete, you will get an error saying that I can't figure out what the time domain of this variable is. All right, and the bottom few equations are related to a controller. It's a simple PI controller. And it starts by sampling the continuous time variable y with a particular sample interval ts. All right, and then that produces a discrete time variable yd. And then I can use that to perform computations. And perhaps the interesting part here is the integration. And in discrete time, integration translates to some form of summation. So the integral state I at the current time step k is a function of the integral state in the past time step, k minus 1, plus the error. Okay, so that's just the basic integration equation in a PI controller. And so on. All right, and if we simulate that, we get the little step response. All right, so I've been talking loosely about clocks and clock ticking and so on. So shall we go into a bit more detail what that means? A Modeling Toolkit model that has a discrete time part, all right? Each discrete time part is associated with a clock. You can create clocks yourself using the clock constructor, but typically you don't have to even do that. When you say sample this variable at a particular sample interval, a clock is created underneath the hood, so you don't even have to create it. But each clock, what it does is that it ticks. All right, and it ticks at certain time points. The default clock is periodic, so it ticks with a certain interval, and that interval is always the same. You can also have a clock with some random jitter in it. Maybe that corresponds to something happens when you receive traffic over the network, and networks are unreliable, so sometimes it takes slightly longer and sometimes slightly shorter and so on. Or you might have an event clock, so maybe when a ball bounces, a clock ticks. Okay, so that doesn't sound like a clock, but it's kind of a generalized clock. It's something that ticks at least. And yeah, I said you can construct them, but you don't have to. So the next step a Modeling Toolkit does when you have provided it with a model is that it performs clock inference. So I already alluded to what that means. It's essentially a Modeling Toolkit looking at all your equations and saying, UD appears inside of a hold. That must be a discrete time variable. And that must result in a continuous time variable. And the differential operator here, D, it also holds similar kind of information. We know that we can only apply a differential operator to a continuous time variable. So therefore, X must be continuous time. Y does not have any such information associated with it, but Y appears in an equation together with X. So therefore, this equation must be a continuous time equation, and therefore y must also be a continuous time variable. So Modeling Toolkit does this for you, and this is what we refer to as clock inference. We infer the clock or if it belongs to the continuous time domain for each variable and for each equation. And the result of that is a list of clock partitions. So it's variables and equations that are associated with each clock, plus the continuous time domain then. And Modeling Toolkit uses all the operators and the shift index to figure out which partitions variables and equation belong to. And as I said before, the transition between time domains is done by hold and sample. And there is actually yet another operator, it's called clock change, because you can transition between two different clocks. For instance, if you want to supersample a variable, subsample a variable, shift the phase of a variable, but maintaining the tick interval and so on. You can all do all these things. I've spoken about this. All right, the next step Modeling Toolkit does after figuring out the clocks is code generation. So the continuous time domain results in an OD, just as you are used to in Modeling Toolkit, but each clock partition results in a discrete time callback. So it's something that is called at a particular time point. You run a computation, update maybe state and parameters, and then the simulation continues. So a little detail there underneath the hood is that the discrete time state is in Modeling Toolkit and differential equation stored in the parameter object. So the parameter object in Modeling Toolkit has been expanded into its own custom data, like a struct that maintains what you consider to be the parameters of the system, but also the discrete time state. The key thing is that it's not part of the continuous time state, so it's not what the OD integrator needs to be concerned with when it performs the integration. All right, so how do we implement generic discrete time components in, for example, a model library? So in Modeling Toolkit standard library, we have things like integrator, derivative, transfer function, state-based object, and stuff like that. And we can create such a standard library for discrete time components also. But when we do that, we don't want to make a choice of a clock, because the user is supposed to choose the clock and the sample interval and so on. But we might still want to be able to refer to aspects of that clock. For instance, what is the period of the clock? So here we see an example. It's the standard library definition of a discrete derivative. When I say discrete here, it should always be discrete time. So it's discrete time derivative. And we see that a discrete time derivative is like a finite difference, right? It's the difference between two values. It's the difference between the value of u at the current time and the value of u at the time point before, divided by the duration of the sample interval. But we haven't specified what the sample interval actually is here. And that's where clock inference comes in again. After Modeling Toolkit has figured out this component is used with a certain clock, that clock is specified externally to the component, but grab the sample time and put that into the variable TS and then use that in this equation. All right, and I can just share a bit of best practices I've figured out while implementing this standard library. We see that I have a block here called structural parameters. So these are not parameters in the Modeling Toolkit sense of a parameter. Instead, they are more like function arguments when you create the system. It allows you to modify some aspect of the equations. And I include both the sample time and the shift index as structural parameters with defaults. So if the user just instantiates a discrete time derivative without specifying those, the defaults will be used. But this also gives the user the ability to override the sample time, should they desire to do that for various reasons. Or be able to overwrite the shift index by providing a specific clock to choose a point in the model at which to specify the clock. If you don't use that, the clock is inferred based on the context. How is this component used together with other components? Key is that the clock is specified somewhere in the model, but only at one location. All right. Can we have multi-rate systems? Yes, we can. I have alluded to that before. We can have a system that includes many different clocks. So here we have a very similar system to the one before. But I have created two variables here at the top, TS1 and TS2 for two different sample rates. And then we see down in my controller, it now says sample y with an interval of TS1, all right, and sample y with an interval of TS2. All right, TS1 and TS2 are different, so this creates two different clocks. And then we perform some computation using the sample values. And we see the result of simulating that on the left. And I've indicated the clock ticks here with dashed lines. And they are using colors. I hope you can see that. So we have one clock that ticks every 0.3 seconds. And it changes the behavior of the continuous time system in a particular way. But then every 1.1 seconds, the green clock ticks. And then we have a completely different change. So you can do things like multi-rate systems. You can also change the clock of a discrete time variable to a different clock, and you can use this to increase the sample rate, or decrease the sample rate, or just change the phase. So here we have an example where we change the phase of a variable. It's a very simple simulation. We just have two discrete time equations and a continuous time equation. And the two discrete time partitions interact through this clock change operator. So we say we have a variable here belonging to clock 2, but we change from clock 2 to clock 1, and it's now available to use in the first discrete time partition. If we hadn't included this clock change operator here, Modeling Toolkit would say clock inference exception. I can't figure out what the clock for X1 is because it looks like it belongs to two different clocks. So you have to be explicit about what is your intention here. All right, standard library. So I have alluded to the existence of such a library. It does exist. It's open source. It's available at the Dinosaur there. It includes things like a delay component. So a delay in discrete time is just a one time step delay, but it's generalized so it can be as many time steps of a delay as you want. There are integrators, which in discrete time is summation, but you can discretize a continuous time integrator in multiple different ways. So you can have a backward discretization, a forward, or a Tustin approximation, and so on. There are derivatives, PID controllers, a sample and a hold, of course. I show here in gray transfer functions and linear state space objects because they are kind of implemented, but they don't work yet. So, yeah, work in progress. And there are also noise sources. And noise sources in discrete time are easier in some sense than in continuous time. Because in discrete time, when the clock ticks, you just draw a random number, more or less, and then that's your value of the noise. And that's very useful when you simulate things like measurement noise in a sensor. So a sensor is taking a measurement at a particular point in time, and it's always associated with some noise. So we can model that also. So can we do non-trivial things? Yes, we can. On the QR code there is an extension to a tutorial from Modeling Toolkit standard library. It's a DC motor that has a velocity controller. And here I've extended it to also include a position controller. So you can do things like that. And I say here I wanted to actually make this a multi-rate system, but since this is work in progress, that did not work. So now the position controller and the velocity controller are the same. But what we see in the plot here is we have two curves. The blue one is the original tutorial from Modeling Toolkit standard library, where the controller is implemented in continuous time. We have a step response here in the beginning in the reference. Okay, so we have some overshoot, but then it meets the reference. And then there is a step in a disturbance torque after 2 seconds. And the controller, having integral action, it managed to reject that disturbance completely. And when we implement this controller in discrete time instead, with a particular sample rate, we see that there is a slight degradation in performance. We have a slightly larger overshoot, and this disturbance is also slightly larger before it's rejected. And that's kind of expected, right? Because the continuous time controller, it sees the disturbance instantaneously, whereas a discrete time controller, it takes a while before it actually sees the disturbance. All right, so this is very useful to verify that when we have taken our maybe continuous time design of a control system, does it work when we implement it in discrete time? And if it doesn't, maybe we have to do something about that. All right, is there documentation available? And the answer is yes, and kind of. So at the QR code here, there is the documentation, that is available in Modeling Toolkit. It's very incomplete. It just gives you kind of the overall idea, but you can check it out already today. Then there is documentation available in modeling toolkit sample data.jl. It's available on GitHub, but it doesn't render because it doesn't actually build yet. So you can read the source files, but it's not going to be very interesting to you, perhaps. But if you're interested in this topic, you can perhaps go and check that repository out, and hopefully within short it will be released. Can you make use of this today? Not really. It's still a work in progress. So I show a dragon here. There are lots of dragons. You're going to get the wrong answer if you don't know exactly where the bugs are. But hopefully within a month or so, you can actually make use of this. And we will have a release, and I will announce it on Discourse and so on when that release is made. It currently requires the proprietary JuliaSim compiler to compile correctly. There is kind of a compiler in Modeling Toolkit, but it will in certain cases give you the wrong answer. So what we have done there is we just give you an error message for now saying that it's not fully supported. But it's still, JuliaSim compiler is free for academic and personal use. So if you belong to the group of academic and personal users, you can already use it for free. There is a standard library package. It's called Modeling Toolkit Standard Library. It's available on the QR code in the bottom there. And it's not released yet, but it's available. And in the end, I would like to acknowledge the people from the Modelica language who have actually done a very nice design. They are in their second iteration of discrete time systems, and we borrow a lot in our design from their second iteration. So if you're familiar with the clocked semantics of Modelica, you will recognize at least a lot of the kind of look and feel. And I would also like to acknowledge Ayush and Yingbo, my colleagues here, who have been working on lots of the implementation that underpins this functionality. And before we end, I would like to make a teaser here. There will be future work. So what you see in the animation on the right is a finite state machine implemented in Modeling Toolkit. That exists already today, but it's still not released. So hopefully within a year or so, we will have that kind of functionality as well. And we see an automatically rendered diagram on the left-hand side of a state machine that have multiple hierarchies. So we have states that internally contain state machines and so on, and you can transition in between them. So there are lots of things happening on this front, and if you are curious, come and talk to us at the Julia Hub booth, or send an email to me, or open an issue and complain about how we have bugs and so on. All right, thanks.
All right, thank you so much for your talk. And as usual, does anyone has questions? All right, lots of questions.
Hi, thanks for the nice talk. I was wondering, how does it scale, like the clock part? So, say for example, I am building a team of robot soccer players, and I need to simulate 22 clocks, which are all actually ticking at the same time. Will it like make 22 callbacks, which doesn't scale ideally, or does it bundle everything into one callback?
If the clocks are exactly the same, they will be considered part of the same clock partition, and it will result in one callback.
And is it then, if you give multiple things like equal clocks but not identity clocks, like different objects but same content, will that also infer?
It determines equality between clocks based on whether their interval and their phase are the same. So you can't have clocks that have the same interval and the same phase, but they are different.
Okay, yeah, that's clear. Thanks.
Hello, thanks for the talk. I have one question. Is it possible inside, I don't know if Modeling Toolkit or this package, to call complex functions with only discrete variables? Because sometimes when you're modeling the sensor output, just the noise is not enough. You have to go through a very complex situation. So is it possible to call this function and assign it to a variable and then go on with the system or not?
Yes, just like in the rest of Modeling Toolkit, you can, if you can't trace through the function with the Modeling Toolkit variables, you can register that as an atom in the language. And then the call to that function will be represented symbolically. And then when you generate the generated code will call the function. But the symbolic language will just treat it as an atom that is not to be traced through.
Okay, thank you very much.
Yep.
Thank you. So if I understand well, the shift index will create a relation between indices and the time steps, and you can use different clocks and custom clocks. So can this be used for event handling? So this is my first question. And my second question is about the solvers. So how the solvers behave when you start having too much of these discrete states.
Yes. The answer to your first question is yes. So I mostly talked here about periodic clocks, clocks that tick with a certain interval. But I alluded to very briefly that you can have something like an event clock, where the tick of the clock happens when a certain event occurs. For instance, if I drop a ball, when the ball hits the floor, that can generate a tick of a clock. And you can use that to do event-based programming. So you can actually, well, I said you could, but in the future, hopefully you can use things like the state machines I have in the animation here to describe things like some continuous time systems require state machines to handle the fact that the dynamics change when something happens. If I have, for instance, two objects like this, they have each have their own state, position and velocity. Maybe they collide in a way that they stick together. After that, you have fewer equations. All right? So that's a little state machine that transitions from being decoupled to being coupled. All right? So today, we can't model that using this functionality, but the idea is to eventually be able to model that kind of functionality as well using this. Yeah. And your second question, can you please remind me?
The solvers.
Solvers. Okay, so it uses exactly the same functionality as if you had written a discrete time callback yourself using the diffeq callbacks library. So the solvers will stop at the tick time. It will launch the discrete time callback, and then they will restart after the callback with a new updated state and parameter vectors and so on. And if you have a lot of these callbacks, obviously that can become expensive, especially if you have a very fast-running controller. Maybe you have a control system that runs on a kilohertz sample rate, but your continuous time dynamics have very slow time constants, so your sample rate is overkill. Then you spend a lot of time and effort actually just running the control system, so that's expensive. In situations like that, it's sometimes beneficial to have two versions of the model, one where you actually have a continuous time controller, so you kind of ignore the discrete time effects, so that the solver can use adaptive time steps to make quick progress in the simulation. And then when you want to analyze the effects that your discrete time control systems have that are different from continuous time controller, then you switch, and then you pay the price to actually run the high sample rate controller. Does that answer your question?
All right. I think this was the last question, and we'll take a break till 11:40, and then we come back here for another talks. Okay, thank you.
Thanks.
I think you can also just plug it in here. I'm not sure how.
Or to use this one? What do you prefer?
I don't know. None of the speakers really used it, so I don't really know how.
Yeah.
Oh.
Well, I'm kind of deciding whether to use my or.
I think it might be easier. I don't know.
It seems like it works quite well. So it's just HDMI.
It's just HDMI. It's just plug in HDMI. Oh.
I mean, my provision is after and I also my sound cam, so I think I need it.
Hi. Yeah, I think everybody so far used just their own laptop. Yeah, but I will just, because the next two talks are 10 minutes, so by the end of your talk I will probably already set up your laptop, so because last time it was already like yeah, it was yeah, let's set up that one, but we also don't have a break, so
Standard.
how are you?
Good, presenting now.
Oh, okay.
Like,
yeah, 30 minutes.
Yeah.
Hi, I'm your moderator.
Yeah, this
I'm so cool. Oh, I'm
What kind of mic do you want to use? I have ear mic,
I
don't headset, hand mic. No, just do the easiest one.
That's this one.
Yeah, yeah, it's fine.
Oh,
yeah. All right.
I have timeline and it's like 28 minutes.
Okay.
You know, a little bit on the edge, but
Okay, so now I suppose I guess we'll go shorter on questions.
yeah, it's fine. I also like lunches afterwards, so
Yeah.
like people can
I think for you it's less.
yeah, than the 10 minutes. All right.
I have like two cards and I will show you. So you have 10 minutes presentation, but I will leave 2 minutes for questions.
Okay.
And then
What are the cards for?
Yeah,
Oh.
so like to remind you of time.
Oh, nice.
So,
okay, I have to stop at the red.
Yeah.
Okay, that's great.
Yes.
What's your name?
It's Evgenia.
Oh, okay, nice. Thank you.
Is there any way you would like to be introduced, or?
No, you just
Okay.
don't worry. Let's just there's only 10 minutes, so we can
Okay,
just
okay.
yeah. Thanks. Thank you.
Yeah, so people talk about they want to do code generation. And what is it you want to generate code? It is the discrete time. You never generate code. You never generate for immediate changes to effort because that's rational. You want to generate code for the controller and the controller. So, and that's kind of a nice little, if you can implement your controller entirely, that's big. But Molly Toolkit is such a limited version of Julia that actually generating C because you have a symbolic language. You don't need to map the entirety of Julia, which is infinitely complex, right? Not to C. You just need to map the very limited symbolically representable programs into C. That already exists. Yeah, I also recall that like
Oh, I think so. I don't know. Let's try to check. Yeah. Seems to be fine. Okay. Can put it out for a while.
They are not very far apart. They are. You say not half like
guest from the Julia Hub sponsor. I have a little pen with my and already that signal system has it starts out by, when you turn it on, it is calling itself to calibrate the sensor, all right? So it goes to one endpoint, resets the sensor, goes to the center, swings up, and then stabilizes. That's already 4 different stages.
Okay, so can we start?
We need to wait for online audience, but 40 is in 10 seconds, so yes.
Always have like it's on or it's not on, or maybe it's a startup phase.
It's not on a screen, so. Oh, no.
Perfect.
All right.
So good morning. Yes, please.
All right. Good afternoon, everyone, and still morning. And we're going to start with our talk from Ivan. We're going to talk about profile likelihood in Julia. Let's welcome him with a round of applause.
Thank you. Thank you very much. Indeed, I am Ivan. I work as a researcher and developer at InsysBio, and I will speak about profile likelihood, practical identifiability, and this talk is somehow linked to the systems biology session we'll have, but in general, those methods are not limited by systems biology field and can be used wherever you have a model and you work in maximum likelihood estimation paradigm. So I'm going to speak about profile likelihood in 3 aspects. First of all, what is it and why is it important? Secondly, what do we have? What are the current state of art methods? What do we have in Julia? What are we implementing right now? So practical identifiability is commonly compared with structural one, and nice excuse to advertise the work of structural identifiability.gl once again. But if structural identifiability focuses on the structure of the model with all available data, practical identifiability studies the precision and possibility to estimate the parameters with the data we have. There are many methods to study practical identifiability. You may have used Fisher information matrix, Bayesian approach. There are certain reasons why profile likelihood is sometimes preferred, even though it's a very computationally demanding approach. I've came up with at least 3 reasons. First of all, it's one of the most reliable ways to study practical identifiability because you kind of get the physical shape of the likelihood function around the optimal value. Secondly, with certain caution, it can be used as a proxy to study structural identifiability too in the situations where structural identifiability methods are not applicable. And it can be also used to study more general statistics like prediction confidence bands, validation confidence bands, and so on. That, to my mind, makes profile likelihood methods a rather powerful tool. So this picture commonly, from a classical article, commonly illustrates what is it about. So you you fix a parameter of interest and study to the left and the right direction whether it intersects a certain confidence level, then it's identifiable, or not, then it's not identifiable. I've listed some packages in MATLAB, R, Python, which I'm aware of and which we used to study profile likelihood, and also 2 packages I'm aware of in Julia. I'm aware about the first one because I've participated in this implementation, and it was implemented about 3 years ago, I think, to prove an article we published about profile likelihood method. It hasn't been updated for a while, and now we desire to renovate it completely, and I'll speak about the methods which are drafted there. The second package, it implements the basic profile likelihood.gl, implements the basic stepwise profile discovery. It also, I didn't test it much, but it also has nice functionality around discovering the confidence regions and 2-dimensional areas. So I'll illustrate the methods we implement right now by an example proposed by Maurice Eisenberg to study profile likelihood. It's a small model, a taxol treatment model, which is a chemotherapy drug, but that doesn't really not important for us now because we are not about biological sense here, but about the methods. And we'll study one of the parameters of this model, which is a sensitivity of proliferating cells to this drug. So the most basic approach, which can be implemented in a while loop, as the name of the room suggests, you fix a parameter of interest, you make small steps to the left and to the right of it, and re-optimize all other parameters. So with this model, it works fine. However, it is a very computationally demanding approach because the smaller steps you make, the more precise your estimation is. At the same time, you need to make hundreds of optimizations, and here we are measuring the performance of methods by the number of likelihood function calls. So a natural way to speed it up is to make this step adaptive. There could be multiple strategies implemented in different packages. So here thank you, kind of linear extrapolation is proposed when you have certain knowledge about the previous fields and you target some reasonable values of likelihood functions to make steps adaptive. That already gives you a certain increase in time. But if you look at what is happening here, you may say, well, it looks like we are integrating an differential equation system, so we are kind of following a certain trajectory and making some steps. And indeed, another way to approach this problem is to obtain the profile as a solution to the differential equation system. The system itself is derived from formulating this problem as an optimization problem. I wouldn't go into details how it is done, but there are certain articles. And it seems like a great advance because you no longer need to optimize, run hundreds of optimizations. You just need to solve a differential equation system, which people kind of know how to do it, especially in Julia. But in fact, the system is not that nice. In general, it's a differential algebraic system with a non-constant mass matrix, which is the Hessian of the likelihood function. If you study not the functions of the parameters, but the parameters itself, the system is a bit less cumbersome, but still you either need to solve it directly, compute the inverse and transform it to ODE system, compute pseudo-inversive Hessian is not invertible, and so on. But with this model, it works great. It gives a great speed up. The steps are adaptive, and the profile is nice and smooth. However, if you don't want to deal with Hessians, a commonly used trick is to simplify the system a bit and replace the Hessian with something more friendly. I'm not going into details why it is possible, but you can use a certain correction factor to assure that you are staying on the path and get rid of the Hessian. That is sometimes the most speedy method. However, the trade-off is accuracy because you can get off the true profile. You either need to adjust this correction factor, and it is a nice kind of problem, how to do it smart, or to run re-optimizations after each step of the integrator. Then this method is something like an adaptive step method. So the third idea to address this problem was proposed long ago. It's the idea to focus more on confidence intervals estimation rather than profile discovery. And the endpoints of confidence intervals are described by a certain system. The authors of the paper proposed their own approach. We kind of also proposed our approach to solve the system by an optimization procedure. We published an article and implemented this likelihood profiler package. It outputs the interval itself, but also we can construct an adaptive grid to recover and the shape of the profile and assure that we are on the right path. However, the original implementation relied on this enveloped augmented Lagrangian, and it didn't really correspond to the termination criteria required by the method, and that made usage of this package sort of an art, and we received certain comments about its usability. So now we, with the advances in optimization.gl, we are re-implementing this method too, and it will be in this new release too. So to sum up, those other methods are now drafted in a separate repo. They'll be in likelihood profiler to version. I think that there is no golden method here, but the power of profile likelihood approach comes for mixing them together and trying this, trying that. You tried integration, now you change to optimization and so on, and that's why we want to have it together. And the last message is that even though it has been studied for a while, there is much more to optimize here, and Julia's CML can bring a lot of power here. So once it's released, I will be very grateful for your benchmarks, use cases, issues, and any help. So thank you very much.
Thank you. I'm afraid we don't have time for questions.
I'm very sorry, but I'm available here
yeah,
for the rest
so
of
maybe
the
questions during lunchtime is a great option.
Thank you.
All right, I'm gonna already introduce our next talk by Chris, and it's gonna be about enhancing the analysis of thin walled steel structures. Very curious what it is about. Let's give a round of applause.
Thank you, everyone. It's nice to be here, and I'm representing my small software company, Run to Solve. So, what we work on is this commodity here, steel. And how many? I'm wondering if you all even have an idea how many tons of steel are sold like this as coils, like around the world. Anybody have an idea? Like Europe or U.S. or in the U.S. it's about 100 million tons a year is formed into buildings or roofs in the US, and it's something similar in Europe. And so we usually sell this steel at about $1 a pound. So if you do that math, it ends up being, that's maybe like $2 billion, $3 billion, $4 billion a year. It's a huge market. And what's interesting is, so what we do with this steel is it comes like this, and then what you want to do to make it into buildings or shape it like this. So when you shape the steel like this, it's very fun, interesting. There's an infinite number of shapes, but with that comes like some overwhelming engineering choices, like what shape should it be? What's the optimum shape? How does it behave? So that's what my company has been working on since 2019, I would say. And we ended up working with Julia just because, so the behavior of these, so we go from the commodity steel, the 100 million tons of it, to shapes like this, and then we want to try to understand how it behaves, and we need to solve equations like this. Just for a single member, it's something like this. Like the thin-walled part of it makes it complicated. And then, of course, like you have, this is just for one member, like one column or one beam. Then you have a whole building, and it becomes like a very interesting problem with like also considering wind and snow and everything. Like, so when you start combining everything, it's a very challenging and can be a very large problem to solve. And so that's why we went to Julia. And so over the last 4 or 5 years, we've written a bunch of packages that I think probably maybe not many people in the world even know about. Like, they're out there. I've listed them to the right, but things like just solving the behavior of a beam or a column, or characterizing the properties of a cross section, or like even interacting with commercial programs, like maybe some of you have heard of, like Abacus or LS-DYNA or ANSYS. Like what's interesting to me is that when I come in here and talk and listen to all of the SciML talks, like the tools that everyone is using for SciML are actually like very useful for solving these structural building large-scale problems. like the nonlinear solve, symbolics, solving differential equations, and even connecting to services like AWS. So like if we're writing, putting our Julia stuff into containers and interacting and saving things, the S3 buckets, like we haven't even have the SDK for that, and like yeah, so it's anyway, like so there's actually quite a bit of like capabilities in this realm now, and I'll just show an example. So I highlighted thin-walled beam. I mean, it's just a few lines of code, like where we take the system of nonlinear, it's nonlinear differential equations, like fourth order equations, and we just write them. It was a little bit of a challenge. I'll have to say that differential equations.jl did not work exactly correctly, or not correctly, but like well for us. Like I had to do some modifications, like do more like finite difference stuff to like get to the governing equations, but I can get them, and then I can solve that system of equations with the nonlinear solver, and I can get the answer, the deformation of a member, and it's awesome, and it's pretty fast, and it's like yeah, it's amazing, and I couldn't quite do it in other languages, so it's great. And we can do cool things like this. So this is like a hat shape that would be, there's probably hats right above us in the ceiling here. And like we can get the buckling behavior of it and display it with awesome programs like Maki, and like and all of this is now like moving, like, so it's been 4 years now, and now we're like actually producing production apps. We're selling APIs like that predict this kind of behavior. We're getting some like web apps. This is just one example of a roof. So like roofs are like a huge market around the world, metal building roofs. And so the back end here is a Julia in a container, and even racks. Like when you go to like the grocery store or a Costco, like there's Costco's in Europe and everything, right? Or where you all live, or like those stores, like those what do you call them? Like hardware stores where like there's these really tall racks with stuff stacked on them. Like that's a huge market around the world as well. And so there's Julia code predicting the behavior of those racks, like the design and helping with the design of those racks. Yeah, so I would say like overall the goal now is like we have these APIs running for single members and some systems, but like the exciting part of Julia is like trying to do more of the high performance stuff and tackle that big building that I was showing you before. And so I would say maybe the next 5 years we'll be spending trying to address those like bigger structural system problems. And thank you very much.
On time for questions. Anyone questions?
Don't be shy. I'm a very nice guy.
Just a question a bit more about your organization. I was curious whether you had given your, I don't know, the size of your team, whether you went through a fully integrated vertical integration of Julia, or you're more in interrupt kind of fashion, and if you could discuss a bit more how you approach this integration of Julia in your enterprise context.
All right, I mean, there's so much to talk about there, but like, what can I say? So the team is, we're engineers. Most of us are academic like style engineers with coding backgrounds. We have recently hired like full stack developer to help with web applications. So like, but we're almost always taking the Julia stuff and putting it in a Docker and running it as an API. Like that's what we found is the best way. Because if I start talking to so I work with big steel companies, and if I go talk to their developer teams, they often are like, "What's Julia? I don't know. I don't want to get involved." So how we get around that is just we run the APIs for them, and then they don't. We just offer the answer. So that's pretty much how we have succeeded, I would say.
All right, we have room for one more question. The longer we think, the less room we have. I think maybe more questions during lunchtime.
It's okay. Actually, my wife is here. Thank you for coming to support me. We're on our way to Dusseldorf after this, and then we're headed to Bodrum, Turkey. So, but I won't. But you can always find me on GitHub, LinkedIn, the Julia Slack, whatever. I'm happy to answer questions.
Okay. Thank you.
Yeah.
Alejandra. Can I move around or I just like...
I can give you this microphone.
Then it's fine.
Hi guys, and we're gonna have our one before lunch presentation, and it's gonna about modeling population dynamics, and Alejandra is gonna tell us more about it.
Okay, hello everyone. My name is Maria Alejandra Ramirez, and today I'm gonna be talking about modeling population dynamics with Julia. So overall, the question that we're interested in is how does a population with interacting individuals evolve over time? This is a very interesting question for many different disciplines. So for example, in ecology, when you have different species that interact with each other and are competing for resources, you would like to know how the system evolves. Also, for social sciences, when you have different types of behavior that are competing, for example, for power, then you want to know how the system evolves. Also in economics, when you have different types of agents like households or banks or companies that have different strategies and they come together in the marketplace, you want to know which strategy is the better one when you have conflict of interest. And in computer science, when human agents and artificial agents come together, you want to know which strategy will perform better in the long run. Of course, this question is interesting for many more, many more disciplines, and for this we're going to be using this package, dynamicalsystems.jl and agents.jl. These are going to be very useful packages to solve these type of questions. So just to have kind of a way to go, I'm going to be talking about evolutionary game theory. This is a mathematical framework that models evolution of populations using game theory principles. So this is going to be very useful when you have a population with different agents that interact with each other and you want to know how the system changes over time. So in this example, I'm going to have two different types or two different strategies. I'm going to use this word like having the same meaning. So we have type A and type B, or strategy A and B, and we're interested on how the system changes over time in terms of composition. So we're interested in frequencies, in relative amounts. So in this example, the frequency of A is 0.4 and the frequency of B is 0.6 because we have a total population size of 10. So we have a normalization condition. The sum of the frequencies should be equal to 1. And then you need for these strategies or types to be interacting with each other. And there is where we're going to use a payoff matrix of interactions. It's going to tell us the outcome of the different interactions, and you read it by rows. So if I am individual type A, I read the first row. But if I am individual type B, I read the second row. So if I am A and I interact with another A, then I get lowercase a. If I am A and I interact with B, I get lowercase b. And likewise for strategy type B. So the core concept of evolutionary game theory is fitness. The higher the fitness, it is more likely for this strategy to have evolutionary success, higher probability of evolutionary success. Meaning that if you have a higher deterministic, of course, but you need a deterministic approach because this is going to be tractable in terms of mathematics. You can easily solve this because it is represented by differential equations. Typically, you have nonlinearities, so you need to solve this by computers. So you're going to solve this numerically, and you're going to solve your ODEs, and for this, the package dynamical systems, it's going to be very useful. For the stochastic description, you would need to use an agent-based model. So you will do a computer simulation generating random numbers, and for this, the package agents.jl, it's going to be very useful. So let's go to the deterministic description. For evolutionary game theory, replicator dynamics, it's very useful. So the way it works is that you have your set of ODEs, and for each strategy, you're going to have an equation. So this tells you the change in frequency of strategy I, so A or B, that is proportional to the current frequency of the strategy and proportional to the difference between the individual fitness and the average fitness. So let's recall that the individual fitness is defined in this way, frequency dependent. It also depends on the interactions. And you have the average fitness, which is basically the average across the population. So the intuition of this formulation is that if your strategy performs well, you're going to have more individuals performing this strategy. So your frequency is going to go up. Well, if your strategy performs poorly, then your frequency is going to go down. That's how it works. So you have your set of differential equations. We have the assumption of an infinite population limit. We're going to have two different types, A and B, just for the sake of the example. So this means that we have two different equations that we want to solve, and we're going to use dynamical systems. So the way it works is that first you need to have the package, so dynamical systems. Then you define your dynamic rule. So the way to go is that you define the state of your system. In our case, is XA and XB. Then we have our parameter, which is the payoff matrix. And then you go ahead and define your system. So in our case, we use the properties of matrix multiplication to define our individual fitness and also the average fitness. And then we go ahead and define our equations. So as you can see, the code is very simple and very similar to the mathematical notation. So it's quite straightforward. In here, you have your dynamic rule. Then you go ahead and define your parameters of the payoff matrix, your initial condition, and then you need to define your dynamical system. This is by a function of the package coupled ODE. You just need to import your rule, your parameters, and your initial condition, and that's it. Then you have a dynamical system that is going to be very easy to use. It tells you the characteristic of your system, so it is deterministic, it is in continuous time, your rule, your parameters. Also, it gives you information of the solver and the precision of your solver. So this works with the package differential equations. So just by adding this piece of code, you can easily modify the algorithm and the precision of your solver. So this will change this description. And then what you want to do is to solve your system. So you want to evolve it using the function trajectory. You're going to evolve it, let's say, for 15 time steps with a given delta t. And then you have another core component of the package, which is state space set, which is basically a container. It's going to make your life easier when you're going to be handling data that is generated by your dynamical system or by, like, through experiments, for example. So just an example. So let's say we have this payoff matrix where clearly type A, it's dominant. So if we solve it, in the x-axis we have the time steps, and in the y-axis we have the frequencies. So we can see that very quickly type A dominates. So here is a schema, a diagram of what this would look like. Then let's look at the opposite example where type B dominates. So very quickly, type B dominates. This is how it looks like. And then a little bit more complicated example. Then you have coexistence where type B just has only a slight advantage. And then you see this very nice outcome in which you don't have a complete dominance, but you still have an equilibrium, but it's going to be a coexistence equilibrium. So of course, these are diagrams because the main assumption is that you have an infinite population. So you need to imagine an infinite population. We have this assumption because, as I mentioned, it's going to make our life easier in terms of math. This is tractable because you're dealing with ODEs. Another example, which is kind of fun, it's the rock, paper, scissors. Maybe you have played this game in your childhood. So the way it works is that rock defeats scissors, scissors defeats paper, and paper defeats rock. You can represent this by a payoff matrix. You read it by rows. This means that you have 3 different equations that you want to solve, and then you have a very nice outcome, which are periodic oscillations. Sometimes rocks dominate, sometimes paper, sometimes scissors, because you have a cyclic dominance, as you can see in the diagram. And this is just to display that you can have a very rich range of behavior, ranging from like just going very quickly to a fixed point, to periodic oscillation, to something as crazy as chaotic dynamics. So to have this, And to analyze this, we use dynamical systems because this is a library for nonlinear dynamics and nonlinear time series analysis. And we want to call it the library because actually this is composed of many different submodels to perform different measurements in your time series. Also, it's a library because you not only go there to pick the functions, but also you go there to learn. There is a very nice documentation where you can learn about these methods, and you also have papers where these methods were formulated and so forth. So if you have your dynamical systems, for example, you can use chaos tools or attractors to analyze your system. When you have your data, like your data generated by your dynamical system or by an experiment, then you can have some kind of recurrence analysis. You can measure fractal dimensions. Also, you have complexity measures. You can perform delay embeddings and so forth. So there are many different functions. You can explore it in the documentation of your package. And if some measure it's lacking, you can still contribute. So it's like, you know, an evolving project. And now let's go to the stochastic description. In here, the assumption is a finite population. Right? We want to make it more realistic, and for this, we're going to use a Moran process. So we have our initial state, and then what is going to happen is that in each time step, a birth proportional to fitness is going to happen. So for the sake of the example, let's assume that type A has a greater fitness than B, so let's assume that we just happen to choose this one by chance, and then what is going to happen is that we're going to have a random death. So randomly, we're going to choose any individual. So let's just happen to choose this one. And then if you think about it, the offspring of type A is going to replace the type B that was chosen to die because the size of the population needs to remain constant. And this, of course, is going to change your population step by step. It's going to evolve it. For the people more familiar with this type of processes, this is a birth-death process. And for this, we're going to be using agents.jl. It's a very nice framework, versatile, very robust, and flexible. The way it works is that first you need to have your package, then you need to choose a space. In here, we don't really need a space, but I'm going to define it because I want to display the nice functionalities in terms of space. And also, it's going to make your representations look nicer. So in my case, I'm going to use a grid space single, where one agent is going to be in each cell in a 5x5 grid. Then you need to define your agent with a macro provided by the package. So let's call our agent player, defining a 2-dimensional grid. And we're going to define our characteristics, our properties of the agent. As you can see, this is very flexible. In our case, we defined strategy and fitness. So strategy would be A or B, and we can define it as integers, 1 or 2. And we're going to have our fitness. If we look into the properties of this agent, what we have is the following, the characteristics that we define, and also each agent is going to have its unique ID and its position if you happen to be working with a given determined space. And then all you need to do is to define your model. With the function provided by the package, you input your agent, which in our case is player, and then you input the space, and there you go. You have a standard ABM, but we have 0 agents. Of course, we would like to have more agents, so what we do is to add our agents. Let's say we add 25 agents, and we just have random strategies. We add them via the function of the package, add agent, and we just have the initializing value of fitness equal to 0. And here we have 25 agents in our standard ABM. So to write this nicer, what we can do is to have these steps like basically collected in a single function. So we do the same thing. We define the space, the model, we add the agents to the model, and that's it. We just need to call the function, and you have your model. So we can rewrite this. And then what we do is to define our parameters. Of course, this depends on which model you're working with. And you need to evolve your system. So we're going to evolve our system as a whole. It's a model step function. And in the beginning, I just have some auxiliary functions that are not really important. Then what we have is the birth-death process. You have a birth proportional to fitness, so you sample proportional to fitness. This is going to be your birth player. And then you're going to randomly pick any individual using the function random agent. And the strategy of this agent is going to now be replaced by the strategy of the birth player. And that's it. That's your ABM, very simple. The final thing you want to do is to visualize your simulation, and for this we use other packages that work very nicely with agents.jl. So we have interactive dynamics, and we need to choose a plotting backend. So in this way, we just have to call a function called ABM video, and then we're going to have this very nice visualization. So in this example, I'm going to show the case where A dominates. So this is how it looks for the deterministic description. I'm going to be having a total population size of 25, and I'm going to show two different initial conditions. So for the first case, we can see how it evolves. Slowly, it's going to be evolving. And then we can see that we reach the outcome. We can also see this as a time series. So we can see how now the stochastic effects, the noise, is going to come into play. And now let's look at the other example where we have only one type A individual. So we evolve it, and suddenly we have a totally different outcome. Because if you only have one of it and suddenly it dies, then you have a totally different fate of the system. So this is why having a more realistic assumption is going to be important. The stochastic effects are going to really determine the outcome of your system. So that's why it's important to use this type of tools. Now let's look at the example of the coexistence. It looks like this in the deterministic setup. And I'm going to show two different population sizes, 25 and 100. So let's evolve them. It's going to, keep on going. We can also represent this via the time series. And we can see that the noise effects are very strong, right? Because we have a population size of 25. But if we increase the population size by 100, then, in this video it's not so clear, but if we graph it as a time series, then you see that the outcome starts to approximate the deterministic description. So this is just to showcase that as you increase the population size, you start to reach the deterministic limit, which is what we expect. So basically in this talk, I went around the question of how does a population with interacting individuals evolve over time. I use evolutionary game theory to approach this question, which is a mathematical framework to model the evolution of populations. This is particularly useful when you have a population composed of different agents that interact with each other and you want to know the outcome of your system. You're interested in the dynamics. We have two different approaches, the deterministic and the stochastic description. They're fundamentally different in terms of their assumptions. So in the deterministic case, you have an infinite population limit. You have this because it is more tractable, and in the stochastic case, you have a more realistic assumption, which is that you have finite populations. So for the deterministic case, you need to solve ODEs, and the tool dynamical systems is going to be the way to go, especially when you want to analyze nonlinear time series analysis. You have a lot of different functions that you can use there. You can go to the documentation and read about it, and actually learn about the methods. And for the stochastic case, you want to perform an agent-based model. And for this, the package agents.jl, it's very useful. It's very nice. And the last comment is that, of course, this is a particular case, but you can use this for any model that you would like to use in terms of ODEs, in terms of a deterministic description, and also in terms of agent-based modeling. You have different spaces that you can explore, different ways of represent your code. So you don't need to do, again, the hard work of coding these spaces or coding the way to visualize all of this, because someone else, in particular, another community has done it for you. So you can take advantage of all of this. So for this, I want to thank the Max Planck Institute for Mathematics in the Sciences and the Max Planck Institute for Evolutionary Biology, because I'm currently performing my PhD over there. And I also want to thank the Julia community because you have been very supportive throughout my PhD. You have made my life easier, especially with these packages. And I want to thank all of you for listening to my talk today. So if you have questions, please go ahead.
Yeah, thank you so much. And I'm going to do the job of microphone handler for everyone who has a question. Oh.
So, hi, thanks for the talk. So I have a question. Imagine we know the final state. If we know the final state, is it possible to get information about what could be the possible payload matrix, or?
Yeah, that's a good question. That's a good question. I mean, so your question is that if you know the final state, you can know your payoff matrix?
Yeah.
In the deterministic description is easier, right? Because it's kind of intuitive, because it's an ODE. But once you have a finite population, it becomes tricky, as I showed case. But I mean, if you know the final state, might not be really useful. But if you have your time series, then probably you can infer your payoff matrix.
Okay, thank you.
Thank you.
Thanks. Do you have an example with 4 species that you can tell us what happens there? I don't know if you have some slide with 4 species, or you can tell us if something new with 4 species, because you showed us 3 species with the rocks, paper, scissors.
Actually, that's my PhD work. So yeah, maybe like reading my papers would be useful. I don't have it here, but basically you can have chaos. Because if you're dealing with a continuous dynamical system, but you can remember and you can recall that in reality we have one less dimension because we have a normalization condition. So if you go to 4 species, then you have a 3D system and a dynamical system. That means that, that chaotic dynamics are possible. But that doesn't mean that you necessarily are going to have chaotic dynamics. You can have this type of dynamics that quickly converge into a fixed point or periodic oscillations. But if you have the right parameters, then you can have chaos. And all the different things that it implies that you have chaos.
Hi, thanks for the nice talk. You mentioned these 2 dimensions, or rather, these 2 ecosystems, one where you model a finite population and one where you model, you assume that the population is infinite. So
Yeah.
is there a way, if you model your system in the finite case, to transfer it to the deterministic case automatically?
Yeah, that's also part of my PhD.
Oh yeah, nice.
So,
cool.
I mean, people have done this already. So you have your stochastic approach, and then what you can do is derive a stochastic differential equation, and then you can also just remove the noise term, and then you have your deterministic system. But of course, you need to derive this mathematically. It's not as automatic or straightforward. You need to like do all the heavy lifting on having this mathematical, analysis on how to go from a stochastic approach to a deterministic approach. Some cases are already done. They're like standard, but others you need to have all this treatment to get them.
I see. Okay, thank you.
Thank you.
It seems that these models are linear model. Does it work with non-linear model for population?
So the question is, does it work with non-linear model?
Yeah.
Well, I don't know precisely what you mean, but for example, the replicator dynamics in itself include non-linearities because, these terms depend on x. So you already have it. It also works with linear systems. I mean, the thing that you're doing is solving ODEs, and then you can use computers to solve them. And that's the framework. The nice thing about dynamical system is that you can analyze your solution further, not just like plot it, but you can like perform hardcore analysis on chaos or, delay embeddings if you have like some measure data. Like there are many different things you can do. Like this, analyze your attractors. this is particularly useful when you have complicated systems like nonlinear dynamics.
Thank you.
Yeah, hi. So if you have like experimental data from the real world about some sort of dynamical system, is there a process that you can do to be able to discover the dynamics of the system involved and the parameters that govern it?
Delay embeddings is the way to go if you want to construct a deterministic system. But also with your data set in itself, you can perform time series analysis. So probably you don't want to reconstruct some kind of deterministic system, you just want to measure some property about the dimension. So for example, fractal dimensions are interested in that regard, or some other complexity measure like, I don't know, knowing how repetitive is a given pattern. So you can perform many different things with your data. So a comment on that is that with state space set, by just having it represented in this way, then you can use very easily all these tools. So it's a standard way to use it. Yeah.
More questions? 3, 2, 1. No questions.
It's okay.
All right, then I guess we can start with lunch break, and then it's 2 hours. And thank you so much again for the presentation.
Thank you.
should we ask the technologist?
Yeah. Because I think they also have some control over
Yeah,
it.
yeah, for sure. Okay, I'll just go. Yeah, okay.
It worked, but it stopped working now. So I don't know if it's.
Because there's only the HDMI here, right? And like the first time, like literally like 3 minutes ago, I just put it in and it worked. And now it doesn't anymore. So just like restart my laptop. Why was it working earlier? So maybe just something on. I'll just give it a. I think there's something.
Maybe on the screens. Yeah. Sometimes it's about like sharing like the first or second screen sometimes.
Let's see what happens. But I can leave the power in. Where was the other speaker?
You want to try, I think?
Are you also speaking?
Yeah.
Hi. Martin. Milan, yeah, nice to meet you. Do you want to already like have a go and just like plug it in to see whether?
Yeah.
So there's this dongle here, for example, with USB-C. Is that what you want to use?
C and HDMI.
Directly the HDMI. Perfect,
Okay,
that
okay.
works. So you can just use yours and you just plug it in. Maybe my laptop after the first screen sharing was like, oh, I don't want to do this
Yeah,
anymore.
no, exactly.
So
I'm tired of it already, yeah.
Just restarting it now.
Okay.
Checking like because my own laptop battery is so shit. I borrowed my wife's laptop.
Okay. There's electricity here in case you just want to like plug it in.
It's fully charged.
Okay. Okay.
But
Hello.
this is good.
Hey.
Hi.
I'm just presenting.
Yes. Yes.
Okay.
Do you want to try to come in here? So yours works fine. It's like let's check. Do you want to use HDMI? Yes. Yeah. Perfect. Put that in there.
Okay. Yep.
Yep.
EC2 Max 0, huh?
That's obvious. Okay.
Also, we like to test mine.
Yeah. Go ahead.
No, but
USB-C?
it's the
Yeah, okay, okay.
So let's see.
Is this guy?
Okay, let's see now. Moment of truth, I guess.
Pretty sure it's my laptop. I should just reinstall the operating system at some point. It's now some 4 years old or so.
Sonoma or
Huh?
are you in Sonoma?
I think so, but I've always just updated.
I mean, it shouldn't make a difference with modern systems, right?
No, my laptop has some.
There's something weird with Mac.
Oh, okay,
no.
no.
my computer.
My laptop sometimes just doesn't restart or something like this.
Okay.
So it has some.
You have the issue talk.
And I think if you do a clean reinstall, you get rid of those issues.
Yeah,
but
that
I
could be
haven't bothered yet. Great. So use works?
Okay, nice.
Yeah.
Perfect. Then, moment of truth for mine.
Actually, I might take mine. Yeah.
Yeah, now it works.
Yeah, okay, yeah. So also the fluttering is a new problem, it seems. It's not the only one so far that has these artifacts, you see.
Interesting.
Yeah. Oh.
Oh.
That's even more interesting. So.
Expert in their own field, not in the other. What do you mean an expert?
Well, oh, okay. Now it's here again. Well.
These are all the mistakes.
You want to just upload your slides on the Slack, and then somebody else will.
But it's really your computer then, eh?
Yeah, yeah, exactly.
You can use mine if you want.
Oh.
Is image like the refresh rate or something?
Yeah, it's weird.
You go down with the hertz.
It's from the
Oh.
I know.
It's more
It's even
worse now, no?
It's even
Worse
better,
now.
worse, yeah, exactly.
Oh, that's going to be low resolution.
Oh, you should.
Okay.
So just like send you the
Yeah,
Yeah,
I have Keynote. I can open it.
I usually have issues with one of the input ports, so I just switch in between.
Yes. Sometimes it's true that like changing the USB-C port.
Yeah, I
changes,
usually.
like,
I mean, I have this
result.
issue constantly. So.
still there, right? The flickering.
Yeah. So try the other one and just. You need both.
No, just charge the other one.
Yeah.
Same.
No, it has the same.
Yeah.
Interesting. So I'll just send you the slides then.
Okay.
Which way? Just throw them into the Julia thing.
Slack will be fine. Yeah, I can easily. Let's see. On the meantime, I can try. Fine.
Okay. No.
Okay, get the flickering as well.
Ah, you get it as well, yeah. Oh, it's also much worse apparently.
But is it?
Oh,
Yeah.
no.
That's fine.
Oh,
that's really bad.
That is very bad, yeah. You wanna change the thing?
You want even change side. I have like 4.
Okay.
But that wasn't the case. No,
No, we started with that one. So if it was there already.
Yeah, we do it.
Yeah, that is exactly as it gets.
You saw that. Can we just try another dongle and see whether it's the cable then?
Nope.
Shit, that's bad. Well, at least we need a computer. I have it on. I mean, for me it's a URL, so I can easily share it. But it's been annoying.
All the experts here. Good to see you. I think you're the only guy who actually could stay seated after a talk and start the next talk directly after.
I thought it was on purpose and it would happen more often, but
Yeah.
What about your laptop?
I mean, yeah. It should work.
Is it annoying?
It is.
Good luck for your presentation. Hopefully,
You can send me your presentations, and if mine works,
I have
you can book Keynote.
Sorry? I have this Keynote. I don't have Keynote though. Yeah, exactly.
it's really nice, this app that you showed with the map and
I mean, Lazzaro has also a Mac, and his was working. So
the dashboard. Yeah.
Your laptop worked fine, right? Because our
it did something exactly like.
Should I try again?
Should I try again just in case?
yeah, I mean, yeah.
Like demoing. No, but I made that for the very first Julia.
Yeah, because I cannot upload the presentation.
I think
we had
it's
used
pretty
this one,
old.
right?
Yeah, we use that one, yes.
And I didn't even make it for Julia I made it even like almost a year before for Klima. Yeah, yeah, of course. Yeah. Maybe it was, so related similar dashboard or something that I looked at.
Are you going to JuliaIO again?
No.
Is it always on the source?
That's fine.
Yeah, it's
So it wasn't because I touched it?
No, but you just need to wait, I think.
Yeah.
But that's fine now.
It's
Okay.
fine. Yeah, he's the only one with no flickering so far for MacBooks.
But it's just because I put some air here from time to time. So get dusty. If it gets dusty, then you can have a short sequence.
But for me, it worked with other. Like, I mean, I never had this problem.
Just blow it.
Okay.
Okay.
But all four of them.
Oh, this takes me back. It's like playing. It's like playing with the Game Boys, you know. That you have to clean again. Yeah. takes me back. It's still
better
like I mean, no, not really.
It's the same.
Yeah.
So weird.
Can we try? I can try again with mine.
Hello.
Sorry. Kind of ran here. Hi, I'm Lisa.
Hi, Lisa.
Hi.
Were you already around in the last days?
I got here yesterday. I've been around, but various things. Yeah.
Cool.
Thought I would make sure. Are we doing like individual computers? Is that
Yeah.
the go-to? Okay, cool.
Trying them out.
Will it work?
Yeah, give it a second. No, still bad.
Same.
Yeah.
Little visual images, and they were not really cute.
Didn't
really get there.
Should we answer that?
January was not the best start.
Yeah, just give it a second because it was operating a moment.
Yeah, we're having issues with Mac.
Yeah.
Okay.
Somehow.
But for you,
I think it's like old.
I have to go to
Interesting. I've been having that.
You want to use USB or you have HDMI on the other side, no?
I was afraid for you.
I have both,
Yes.
I think. I normally use USB-C, but maybe
The new Mac.
it's all USB-Cs, right?
Well, no, like the old one, like yours is
Mine
newer.
is like newer.
So it's better. Like they stay.
Although maybe not.
just give it a moment.
But yeah, you really end up seeing the same thing as I do.
All right.
All right. Yeah.
That looks pretty
It's
constant.
really the dongle.
Great.
Mine? I don't know if you're informed.
Yeah.
Yeah,
Happy to help.
we're trying to move his slides and my slides. I have a link. I can send it to you.
Sure, I'm happy to help.
I think. I mean, actually, I think I have you. I mean, we met at Berkeley. I think when we, with Fernando Perez and Paco, you gave a talk after mine in a classroom.
So whose laptop do we start with then? If it's not mine, because
Oh yeah.
Either his.
I mean, I don't have the keynote thing, so.
or I just like some
I mean, I'm fine.
I mean,
Whatever works. I can. If yours works.
I mean, mine should work, but I mean, if you want to give me your slides as PDF, yeah, because I don't have the keynote thing.
Mine is a link on Google Slides.
And they are all super common.
I remember meeting you. I was in the middle of like qualifying exams, and my brain was like 1/4 there.
I was very happy because like I presented like a Julia thing, and then you just showed up like all this like the Julia model. I was like, yes, that's cool. It was a really cool lecture.
Thank you. Well, we'll do a 10-minute version today. It was funny, for some reason in my head we had 20. So I was like looking last night, and all of a sudden I was like,
Compressing it.
You know that.
No, it's good stuff. Yeah. Actually, I checked a bit of the whole like system and so on. It's very different to what I do, like this, like planet economy and so on.
yeah, it's like the resolution is like completely different. So I feel like the types of problems we deal with are, but yeah, this summer's been fun. I graduated, so I actually have some time now to like.
Congratulations.
Thank you.
Congratulations, yeah.
I'm starting a postdoc, so
Hello.
dig back in. This is like perfect timing because I've kind of been hoping. I like the project we do, but I'm doing
We have like 3 of them. And somehow our laptops were
yeah, like, I
flickering.
want to maintain it.
You won't try
But we're
yours.
not even funding for it, so
So like both.
it's hard to like put too much time and effort into. I'm like, I want to build something new, so I'm hoping to get some ideas. Even in projects like I'm not low on battery, but I don't feel like
The middle is winter.
I'd like something kind of like refreshing. If I'm figuring it out every time.
Yours is also fine.
Fair enough. Yeah.
I just will do anything, but I'm gonna be.
Which
is not fine at Stanford.
Mine, both hours are
Paco's
flickering.
going to Stanford as well. Yeah, he graduated also like in May.
Oh.
Maybe it's the connector. How?
Okay.
No, it's back. Like it was actually for the statisticians, but in the end he got like a position in current sciences.
I should message him because the data science postdoc that he wanted.
I've been to another.
I was talking to him, he was like really stressed.
Okay, I mean, if you have keynote, you can start. You can have this also. No. Okay, so.
But it's funny, like you kind of like say, I say you go like you graduate at the same time, and then you go to this thing.
I'm gonna message him as soon as I yeah, because I'm gonna work with some folks who use like satellite data for wildfire. So I'm thinking I get like I'm gonna and I saw quickly
Yeah, because he's going to be on the earth sciences department now, and also
No, makes sense, understand. Okay, then, so this is not needed, right? This is you don't need this one, right? We do, okay.
So that's yours for sorry?
There's also an PDF. Same, just static. Mic check, 1, 2. Something works. Great. And I think it's full screen.
Are you really reserved to see that? Yeah, I remember the name, but yeah.
Yeah. Do you? Don't touch it or not? Okay. Great. Welcome, everyone, to our Earth and Climate Science mini symposium. It's going to run over the next 3 hours with a little break in between. We have a bunch of wonderful speakers. Each of you will have about 10 minutes, including questions. So it's really about getting to the point, but we will also have 20 minutes at the end as like a discussion, or if any one of you really runs over and we can't get you to stop, then we'll use that probably some of that time. And yeah, the kind of the theme of this mini symposium this year, we kind of thought like, okay, maybe we want to give it like a little theme. And so we thought about this like power to the user, which is really this Julia philosophy we feel like is very evident in a lot of the software that we're building. And I basically just like put a few things together where like I was like, okay, why is power to the user actually really, really, really important? And if you think about like, I don't know, the beginning of computing, maybe like during the Second World War, Turing's bomb, as obviously like, I don't know, if you ever wanted to build let's say like a climate model or so on one of those, you couldn't even, right? Because I think that first one wasn't even Turing complete. Sure, then you get to like the Fortran punch cards, something user-friendly is definitely also not there, where you can really like build something that's super intuitive to use and which really leverages like a lot of power of this computing architecture. Then even like at some point in the, I guess like 60s, 70s, we had like a lot of like go-to statements. I find that still like super confusing to read that. But now we're getting really into this era of like Julia code and things. You can write down things in like really quickly and get a lot of functionality out of it. And so I mean, in Julia, we know we're basically like starting to bridge this whole idea of like, you have like something that's from a computational point of view, really, really efficient, but at the same time, we're also something that's like very expressive. You can write it down in a few lines of code and you write something really beautiful. For Earth and climate, this is obviously super important because we're dealing with a lot of data, often also with a lot of compute somehow behind the scenes. But at the same time, we want to have answers for a lot of people, policymakers, researchers, that are basically, you can quickly come up with an idea and would like to analyze research results, analyze data, come up with conclusions. And so at the very end of the spectrum, I've just pulled up this little screenshot here from En-ROAD, which is like one of these climate simulators where you literally can just like drag a slider in order to simulate the climate. I'm not saying that everything should be as far as En-ROADs, because that's obviously also the stage where you give up hackability. You can't suddenly change it anymore. You can't say like, oh, I want to inject my own piece of code here now. But I guess like somewhere in between the Julia code and like having something that's like interactive and you can play with it is definitely the thing where we're suddenly leveraging a lot of power. Julia enables us to do that. And so this is where exactly in the next 3 hours. We will hopefully hear some amazing talks which show us some cases of how our community has already achieved that. And I hope we will also discuss a lot of like how can we leverage the power of the user even more. So I'm excited, and I think we'll now start with the first talk. And Francesco, you're introducing everyone, right? Great.
Okay, so thank you very much. So just one quick thing for the speakers. I'll be handing out yellow card after 5 minutes of talk and red card after 7. And to warn you about the time. And so it's my honor to introduce the first speaker, Martin, that will talk to us about hydrological modeling. So give it up for Martin.
All right. So, we have 2 speakers on this talk, Martin and Martijn. So it's a bit confusing, but since Martin already had many other talks, I decided to take care of this one. So we both work at Deltares here in the Netherlands, in Delft. And this is a picture from our campus. It's the largest wave simulator, wave flume in the world. We both are maintainer on Julia Geo, helping to build the ecosystem to work with geospatial data. But I'll be presenting on something that we're doing not in our spare time, but really for work. And that's working on hydrological models. So I'll be presenting two models, and after that I'll talk a little bit more about interfaces and how we can possibly achieve this power to the user theme of the session. So WFlow was our first model. We have more than 2 models that we develop at Deltares for different purposes. But WFlow was the first one to be rewritten from a different language to Julia, and overall that's been a big success. So it originally was in Python, but it wasn't quite fast enough. And so RiberSim is what I'm working on right now. So it's more for water resources management. And it has actually a long history being written in Fortran in the 80s. But that code, it just wasn't maintainable and hackable to the degree that we want right now. And for instance, we are redesigning it based also on newer data standards, like the geo package, for instance, which means that if you have a RiberSim model, all the data is in a geo package, which means you can just load it in QGIS and it will show up on the map, and you can see all the data that's in there. So in the case of RiberSim, right, so we have 3 layers, and so it's a physical. We use ordinary diffEq to basically model this differential equation, the water balance. Which is a very simple ordinary differential equation, but the model that we're building will actually be quite large. And here I just show the main distribution network of the Netherlands, but we will be controlling in the order of thousands of more than 10,000 nodes where we control the water balance. And we have separate layers, like a control layer that's implemented using callbacks, and an optimization layer to fairly distribute water between users. That's using JUMP. But this model, of course, because it only models the surface water, but of course it can infiltrate into the groundwater, so we cannot really make a cut there. So in the Netherlands, in Dutch application, we want to couple this to other domain models that take care of the unsaturated zone and the groundwater. And these are existing models that we are not rewriting yet, but they're in Fortran. So we have to couple to them. Yeah, for RibaSim and Wflow both, even though they are implemented in Julia, we basically build it in a way that nobody can complain about this fact. Like we are building executables and that they can use the way that fits in their existing workflow. So for both packages, we have, for instance, Python workflows, Python preprocessing packages that derive the data, and that's also that's existing workflows, but it's also to some degree the ecosystem that's more mature in Python. Of course, we'd like to see that change in the future, and well, that's part of the reason why we're working on the Julia Geo ecosystem. But that's the reality for now. So we're making these executables using package compiler. This week there was talk about Julia C, so we'll be able to get much smaller binaries in the future. So then how do we do this coupling to these other languages? And so we use an interface from the CSDMS, the basic model interface. And that basically describes some verbs for like, okay, this is how you initialize a model, this is how you do a time step, this is how you get the data out. And so that's there's a package basic model interface.jl that's basically just empty function stubs, and that says like, okay, go and implement it on your own model type so that we can communicate. And you can use that in Julia to communicate between Julia modules, but it's basically written for targeting cross-language interop. So in Julia you can have much richer semantics. So for instance, like using the SciML interfaces that would achieve many of the same goals but allow more. And that doesn't mean that you have to use all the SciML solvers, but you could use just the interface packages, for instance, to say to say like, take a time step, give me the data. And so it can really be this simple in this case, because RibaSim is using SciML, and the things like take a time step already works, and in the BMI it's called update. In Common Solve it's called step. So that's I think that's maybe something worth considering. Like, should we start implementing these interfaces to make it easier to work together, basically? That was my talk. Any questions?
Are there any questions? I will be giving out the microphone. No questions yet. Okay. Oh, you one.
It's just out of curiosity. Like, when you have a model like that, do you like also assimilate data into it, continuous, or how does that work?
So for Wflow, we do that. We have coupled it with this software called Open Data Simulation. For RibaSim, we have not done that yet, but that's also, for instance, how you could use the BMI and to do data assimilation, for instance. Yeah.
Okay. Are there any more questions? Otherwise, I think. Sorry, question? Okay.
I guess in the Netherlands we collect a whole lot of data, right, about water.
Yeah.
So how does that work with? I mean, I suppose these models, they are from first principles, like physics, right? But then at the same time, there's all this data about the actual water levels. So how's the kind of calibration process when you make these models work?
basically it's quite a large project because we are gathering all the data from all the water boards in the Netherlands to make these parameterizations, and then we of course try them out, compare them to observations, and right now we are at the early stages to just get it approximately right, and yeah, it's already quite good. So we haven't really started the fine-tuning part yet, but I'd like to see if we can use, for instance, SIML sensitivity to like maybe automate the last turning of the knobs. That would be interesting.
Okay, thank you very much.
All right.
Again. Now we have our next speaker, Ali Reza, who will talk to us about designing storage for rainwater, right? Okay, very nice.
Hi everyone, I'm Ali Reza Shafai, PhD student at TU Delft. I work on multi-objective stochastic storage planning with considering the uncertainty of the demand and rainfall. In response to the high demand and also the climate change-induced impact, the water utilities impose the large consumers to restrict their water. In response to address this issue, the rainwater harvesting systems can be an option in addition to the input from the network. By planning depends on the uncertainty of the demand and also the rainfall. The literatures in this topic mainly worked on use the simulation-based optimization to solve this problem, to find the optimal storage size. But their work has some drawbacks such as interactability or low efficiency and so on. And also, they did not consider the uncertainty in their work. In this work, we want to cover these issues. As they start for considering the operational routes, the flows in the network, we consider the mainly used yield after spillage method, in which you can see the different flows, for example, runoff, the outflow, and the volume of the storage in the network, and S represents the storage size. But the min and max operators in these flows make the problem highly non-convex, and we could not solve this problem to optimality. So we use the big M method, and by introducing binary variables, reformulate the non-convex problem to a set of mixed integer linear equations. And then we formulate the problem in single objective options by maximizing the efficiency, which is defined as the outflow from the tank to the network over the demand of the network, by considering the budget and the cost, and also from the other perspective, minimizing the cost of planning by considering a minimum efficiency for the system. And also we can formulate the problem as a multi-objective by considering both of the objectives simultaneously. So we can introduce the uncertainty in the network, in the problem, by considering the rainfall and demand as the random variables, that their historical data follow a specific probability distribution. By doing this, we can formulate our stochastic multi-objective problem, in which instead of the efficiency, we calculate the expected efficiency over the demand and rainfall scenarios by considering the constraint, the flow constraint. And also, if we want to have a guarantee against the worst scenarios, we need to use a risk measure in which we use the CVAR, the conditional value at risk, which is a commonly used risk measure in the operational and planning problems, in which the decision maker add a value of the risk to their objective function by beta parameter and adjust the percent of the worst scenarios using the alpha. And considering this optimization problem, we can reach to a risk-averse stochastic plan for our rainwater harvesting systems. As the coding in the Julia, we read the data using the delimited files package. Then we define the parameters and initialize them, and for changing between the risk neutral and risk averse, we change the beta parameter to 0 and 1 respectively. And then we import the required package, which is the jump and multi-objective algorithm package. And then we define the planning variables, the binary and control variables, which depend on our rainwater, on the demand and the climate scenarios, and also the CVAR related variables. And then defining the constraints, the set of mixed integer equations as these constraints, and then defining the objective function, the multi-objective objective function as a set of vector of objectives. Using this objective, we use the vector to input the multi-objective problem. Then, and our case study area is a botanical garden in the Amsterdam that we use the data of this area. By solving the deterministic problem in the single objective case, for the maximizing efficiency, we got the high efficiency, but by paying the high amount of the cost. But when we minimizing the cost, we need to pay a little amount of the cost, but we have to expect a little value of the efficiency. But as the scenario, as the input of our stochastic problem, we need to generate scenario. For this purpose, we use the KNMI data and apply their different uncertainties about the temperature, level of sea airflow, and also different level of uncertainty. We generate our rainfall scenarios. And in this figure, you can see the range of our demand and rainfall scenario and the deterministic value that we use as input to generate these scenarios. This result represents our stochastic programming for minimizing the cost, considering a minimum value for the efficiency. As you can see, we get a higher efficiency in the risk averse and risk neutral compared to the deterministic case when we consider the worst case scenario and 8 of the worst scenarios. And also, when we solve the multi-objective optimization, we get a similar result. For example, this, as you can see, this figure also follows the result of the previous table. For example, for the 8 worst scenarios and for the worst year scenario, we have a higher value of the efficiency when we solve the risk averse and risk neutral compared to the deterministic one. As conclusion, the contribution of this work converting the non-convex flow equations to the mixed integral linear programming and for providing a trade-off between the efficiency and cost, and also considering uncertainty of the rainfall and demand in the rainwater harvesting systems design, and also again the worst case scenarios using a risk measure. And also as a future direction, we can consider the impact of the price of water and the water quality issue, for example, defining different index for assessing the quality of water and also reducing the computational burden of this problem using the different approaches, for example, the composition approach. And thanks for consideration.
Okay, are there any questions? I think we have time just for one quick one, but yeah.
Hi, thanks very much for the
You're
talk. I was wondering because like basically in many European cities you have much more precipitation in winter than in summer. So like how do you take that into account? How much does that affect the solutions to your problems?
For this scenario generation, the KNMI data has two different scenarios, one for over all of the year and one for the winter season.
Okay,
and we
so
can
you separate out the winter season, okay.
Two different scenarios for the over all of the year and this winter.
Okay, thanks again. And I think we can go to the next speaker. Thank you.
Welcome.
Okay. And our next speaker, Gabriel, is going to talk to us about flux estimation from flux towers.
Okay. All good. Okay, thank you. So I'm happy to be here. So today I'm going to present you my package on turbulence flux estimation, turbulence-flux.gl. So this is a package for estimating fluxes at high resolution. So I'm a postdoc at the National Research Institute for Agriculture and Environment in France. So let's start with a bit of context. So we have in our lab we have a flux tower, which is in the northern part of France. So it's part of European-wide ecosystem network of flux towers. So these flux towers are particularly important for understanding the different ecosystems that such as the forest, grassland, or wetland. And so it's particularly important to process the measurement of this tower in order to understand how the upper atmosphere exchange matter and energy with the ecosystem below. And behind this exchange, this is the exchange is done by turbulence. So here I just asked a diffusion model to give me some illustration of the turbulence above ecosystems. And so the tricky thing with a flux tower is that you need to only get the turbulent transport that is local to your ecosystem in order to avoid integrating fluxes that come from outside of your ecosystem. So there are standard ways to do this. And one standard way is just to compute the covariance between the vertical wind speed and any scalar, such as gas, such as heat, or such as temperature, or any gas concentration. So the thing is here is that you can see on the gas concentration here that we have some structure in the signal. So we have a low frequency trend that is probably corrupting the signal, and we also have some middle length scales. And if I zoom even more, I can see that I have other structures that are of different size. And the tricky thing is that we have to carefully choose, with this standard approach, we have to carefully choose the average length in order to only capture the turbulent transport. And so this is a kind of a limit to the standard way to estimate fluxes, because by averaging, by using this approach, we do both two things: the separation of scales and the statistical estimation. And if we modify the averaging length, we have an impact on the way we separate the scales, and also an impact on the statistical estimation. And with this approach, we can't get high resolution estimation of fluxes. So getting high resolution estimation of fluxes is interesting if we want to get some, for example, the dynamic of the ecosystem, for example, the conductance of forest, for example. So one way to overcome this is first to decompose, then to estimate. So we decompose the signal into different scales with different, according to different frequency band, and then we estimate the fluxes for each frequency band. So the proposed package here is we propose a general framework for decomposing signals in time versus scale coordinates. So this is something which is known since the 90s for doing this kind of thing. But we integrate also in the package a way to identify the turbulent components in that space. And the way to do this is to use a frame of wavelets with some, since we are doing some estimation of physical quantities, we need to guarantee some energy on correlation conservation. So the frame of wavelets is constrained to have this property. So first we get, here we have the vertical wind speed, here we have the gas concentration. So we make a bunch of convolution with a bank of filters, and then we produce for each frequency band a statistical estimation of the flux in this frequency band. Now I have different fluxes according to different scales, and then I can sum it according to a mask, and the mask here will represent where do I consider that turbulence is present or not. So this approach this is a research work, so we first need to wait for some feedback from the community, but it will be released with the package. So I will start by presenting the goal, and then I will show you some example of results we get. So the goal of this package is to propose a fast and reliable library for doing time versus scale decomposition, because in the literature there was different paper propose different approaches, and I think it will be nice to have something which is general enough and that people can start from this to develop new time scale based approaches for flux estimation. So the features, it will probably change how we compute convolution, but like for now we compute convolution by fast Fourier transform because we have like very big signals. And the wavelets are generated from a generalized Morse wavelet package. So I won't get into wavelets because it's not the purpose of the talk, but this package I developed is already released. And we get some fast enough computation time, so below 1 minute for 24 long fluxes with 20 Hz data. So it represents like approximately 2 million samples signals. And so we also make it differentiable against time averaging on the wavelet parameters, because we wanted to study, for example, the sensitivity of the estimation against the wavelet parameters on the averaging parameters. And also we performed the analysis of the turbulence. So we have a graph structure which is based on graphs and sparse arrays to analyze the turbulence. So in the future, it will be nice to get some new methods for turbulence notification. And as some people was talking about this, so of course to make it a library, to integrate it in existing standard tools, into existing standard tools. So let's start with a bit of an example. So I have some data, so it's a data frame like with some wind velocities, depression, gas concentration. I have my height of measurements, the sampling frequency. And I have two kind of parameters, how I average on our samples on the wavelet parameters. So here the gas concentration and here the vertical velocity. And if I get the time scale decomposed carbon flux, here I have my time scale carbon flux decomposed in time scale space. And what I can see is at the top here is the small scales, and at the bottom the large scales. And I can see that there is kind of a sweet spot where I have the turbulent transport that carries the carbon across the canopy. So during the night I have a respiration, which is in violet here, and here I have the assimilation, and I get also some some structure at the bottom, but I don't know how to integrate it. I don't know if it's part of the turbulent. So we developed the metric that gives us an indication of it. And we can see that it's correlated with the previous pattern I showed you before, that gives us a turbulence mask. And I can use the turbulence mask over the time scale decomposed carbon flux in order to get a time resolved carbon flux with a turbulence mask. So here I have the UC30 is the standard way to do the estimation, and the HRS here is the 10 minutes resolution of our package. So you can see that it correlates well with the standard way to do it, but with higher resolution. And the nice thing is that you can change the length of the averaging length in order to get something which is here less noisy, but you can vary the averaging length. So it's kind of nice. And yeah. So the package will be released hopefully by the end of this summer. And I'm looking also for some contributors. So if you are interested, contact me. Thank you.
Okay, we have time again for a quick question. Or anybody up? Okay, I have a curiosity. So at the beginning you showed the ICOS location and your method you said it's general. Have you tried also validation with like the FluxNet locations globally, or?
So we need to have access to the 20 Hertz data, so it's not always possible to do this from the ICOS data portal. So for now I only tried on our tower, so because we have the data. But yeah, we have to test it on actually on higher towers too, because yeah, it's not the same turbulence. And yeah.
Okay, thank you very much. Okay, next up we have atmospheric modeling with Milan. Exchanging of laptops, I guess.
Is it in Slack?
Yes. Oh, sorry.
Sorry, folks.
This one.
Yeah, good.
Here we go. Yeah, thanks.
Great. I'll just start talking now. Hi, I'm Milan. I'm a postdoc who, well, most of the work that I actually want to present today is work that I've done in the last like 1.5 years or so at MIT. But I moved back to Oxford, where apparently, maybe that was my mistake actually. And here we go. Fantastic. And yeah, I want to present my pet project that I really spent most of my... Come back. Okay. My pet project, which is Speedy Weather. And with Speedy Weather is an atmospheric circulation model. So you can solve the equations of motion, a bunch of different ones we have implemented in order to simulate how the weather over the globe is evolving. And my incentive with this model is that, and that's why sometimes I give it the slogan like play atmospheric modeling like it's Lego, that you, instead of just building another weather forecast model or whatever you want to use it for, to build something where you can very easily plug and play a lot of components in and out and really use it in this idea of like power to the user. Obviously, a lot of thanks also goes to basically try to write everyone down who contributed to this repository in one way or another. And so yes, there's a lot of contributors, even though I think most of the heavy lifting is still unfortunately on my side, which doesn't have to be that way. And so speedy weather's niche is really this, like if you think about atmospheric models, or I think the same probably also holds for ocean models, there is a trade-off between models that are really like complex and physically accurate and those ones that are really easily usable. I feel there's still there's kind of like a niche, a gap in between, where you have a few models that are really developed to be super accurate, run in like big weather forecasting centers, and then there's a couple of toy models, and there's kind of like a gap in between. At the moment, speedy weather somehow still falls into this little gap, but by using Julia and some of the concepts that I will present in the next minutes, I'm hoping to I have already pushed it much more to the usable and extendable end of this graph, and my master plan is that this really becomes kind of like where the power to the user really starts to explode then once it is a platform that people can use easily, that basically its physical accuracy will just shoot up and kind of reach a completely new area in this graph. So where are we? I already talked about speedy weather last year. I realized, actually just looked it up yesterday, that back then we were at version 0.5, now we're at version 0.10, and I actually would like to release the 0.11 also soon. What do we have gained since? I've wrote a lot of documentation in the last year, so I feel like if anyone wants to learn something about how to do global atmospheric modeling, you can almost use this as a textbook and how to understand how we're actually solving these equations, how we derive some of the stuff that has to be derived on the way. We also have a JOS paper out now, if anyone is keen to understand a little bit of our approach to this idea of like, how can I write a model that is somehow extensible, which I believe actually applies to much, much more than just atmospheric models. And so if anyone is keen on that, please reach out. Then a bunch of videos that are produced in the last years. There's one here now of cloud cover. At the moment, unfortunately, cloud cover is still diagnostic, so it basically just checks, okay, where's humidity reaching 100%? It doesn't really interfere with radiation, which is unrealistic. This is something that we definitely have to work on. And I've also run like some simulation at a somewhat higher resolution where you can see humidity somewhat just above the surface being moved around. But there's still a lot of things unrealistic. So in the Amazon, for example, that's this area here. Maybe you've spotted that. There should be a much stronger daily cycle, and that's currently not the case because there's a lot of like fluxes, what we just heard about, that are not done right. Now I see that again. And so to get to this like power of the user, because there's technically like so much complexity, and we built a couple of features in that makes the whole thing a bit more approachable, a bit more like, hey, what can I actually do? So in the case of a user saying like, what can I do and how can I do it? We basically, speedy weather is always, everything is put into this like simulation object. Simulation object is then always split into the prognostic variables that really determine the current state, the diagnostic variables, everything that you have to somehow compute in order to get to your next time step, and then the model is basically everything that's supposed to be constant. And you may ask like, okay, what can I do? How can I do this? And so we even came up with these things like a tree function. And tree function is basically just inspecting your entire tree of this like simulation object, and you can see where different things are. So for example, if you just do the tree, you would see like, oh, in the model I have a planet, and maybe I want to have a look at the planet. If you then basically look one level down, you would see, oh, planet has a gravity. And so it kind of tells you, without actually looking into the documentation, it tells you, maybe you could just create an Earth as a planet, but just set the gravity to 1. This is one of the philosophies that we follow. You could also just, because it's a mutable struct, you could just change it. And you could also just define, for example, Mars as a new abstract planet and just set its gravity to something else to have a new component there. And this is basically how a lot of these components try to work. We try to follow this philosophy all the way through, so that you can just say, you basically just look at how is the model built up, of what are all the components. In the same way, you can basically swap in and out different things as you like. And you can do this in a Jupyter notebook, you can do this in a Pluto notebook, you can do this in your REPL, you can do this in a script. A lot of other situations that we come across are like where some of my colleagues say like, hey, I would love to use your model, but I would like to add this term. So there was a colleague of mine who said, like, I want to add this term S that's like a stochastic stirring term, and here's the equation, how do I do this? And so we try to develop like a philosophy where we say, okay, any term that you can add, there's a certain number of steps that you have to follow in order to do this, and we try to split this into the first step being like the define step. So the term that this colleague wanted to add is basically a forcing. So you basically create a new type, a struct. You could make it mutable or not mutable. It depends a little bit on what you want, but it has to be a subtype of this speedy weather.abstract forcing. And then you would basically throw all the parameters that you need, you would throw in there. So that's this first like define step. Then we always have the second like initialize step. So there's anything you want to do somehow up front. For example, you want to know what is the gravity of my planet that someone else has somewhere else defined. And so you can basically, this initialize step is this kind of communication step between the different model components where you can also load something from file. And then always the third step that you have to define in order to get this in is that in this case, because this is a forcing, you have to extend the forcing method. And there's basically, it's always the same arguments that you have to put in there. And then in this case, because this forcing is supposed to be on the vorticity equation, you probably want to then change the tendency or accumulate into the tendency of the vorticity. And so basically, if you follow this rule, you can basically just, in your notebook, you can just say like, oh, I'm just defining it like this. You hit enter. Some of my colleagues asked me like, hey, if I want to do this, how do I branch off? Where should I supposed to branch off? And I'm like, no, there's no branching off. You don't have to branch off. There's no, it's kind of like a feature. You can just plug that in. You can, hopefully, as long as there's no breaking change, it would even work with the next version. And it's even like supposed to work across different models, because you may say like, oh, I want to add the same term into a different model. So the way you use this is then really just like that you create this a new forcing object. Here I'm just like calling this like stochastic stirring, and you basically just pass that on to the model constructor. And whether you now write barotropic model or shallow water model or primitive equation model is then basically the same thing. This is really the idea behind it. And so in this case, this is actually what it looks like. It was some stochastic forcing that just starts to stir a little bit the circulation of the atmosphere in the northern hemisphere. The next cool feature that we have introduced in the last months is this callbacks that is also quite a famous concept in machine learning libraries. It's basically just the idea that if you loop through something, so a typical time loop you would do in order to solve a differential equation, you have your time step, and the callback lets you inject any part of the code directly after this time step. And so we have again, basically very similar idea. You can, for example, if someone tells me like, oh, can I assess the mass conservation in the model? I'm like, yeah, you can just define a mass conservation type. You make it a subtype of an abstract callback. You can throw in there whatever you want. You have to define the initialize function. You have to define the callback function, so what it's supposed to do on every time step. And in this case, even you can define the finish function, whatever you want to do at the end of the time step. For example, save something to file. And this is, for example, also how we implemented a particle tracker, where you just say like a particle tracker at the end of every time step just tracks, okay, where are all my particles now? And this way you can basically just store their location. And it's a very general way of injecting any code. You could also define like, oh, at, I don't know, at 2100, I want to suddenly change the land-sea mask and let basically the entire planet be flooded, because you can just say as a callback, you can just inject that, conditionally check when it's supposed to execute, and then change something inside the model. That's not a problem. I'm going to skip over this. There's a few like little things that I always find helpful, but just to basically finish up with the roadmap, the things that we're still working on is like there's a lot of things around physics, like more realistic radiation that we have to get in, different ways to represent climate change, sea ice, ocean. I would love to also support more exoplanets. So basically, at the moment, the Earth is not hard-coded, but it's not really tested much on other planets. There's a couple of numerics things that are basically open issues. A bunch of software stuff, like how do we best do the data output. And there's also a bunch of computing stuff that is currently higher up on my to-do list in terms of like GPU computing, which we're like hopefully halfway there. And then also what everyone is always waiting for, enzyme to be there, so that you suddenly can actually really get more machine learning into your models. If you're interested, have any questions, any ideas, suggestions, really our point of contact is just the issues, so you can always feel always free to just throw in any ideas that you have there. I hopefully will respond in almost no time, and thanks for listening. And I'm excited for the next talks as well.
Okay, time for a quick question, I think. Just one? Oh, okay, oh, there are a lot of them actually. Okay, sorry. Okay, please.
There are no oceans in Mars, but there were in the past. Could you simulate them? Tell us what it was like.
Guess what? We have a no ocean type. You can just say ocean equals no ocean, and guess what it's doing. Sorry?
Could you tell us what it was like in the past when there were oceans there?
On Mars? Yeah. I don't even know. I know that the orography of Mars is like influenced by like previous oceans, because you can see these like how like water masses flew down there, but I actually don't know.
But your model would tell us.
No. I mean, no. It's still like atmospheric circulation. It wouldn't actually simulate the ocean. So the ocean in our case is always like more like boundary conditions. There is plans to go towards like coupling with like oceananigans. I'm looking at some people there who can probably already come up and swap the laptops. There's some plans to like really build an interface so that you can easily couple to other ocean models that actually dynamically solve and not just like thermodynamically do something with the ocean. But it's a longer story and it's a bit of a bigger one.
Okay, I think for the next questions we will need to wait for the break. Because next up we have fluid dynamics in the oceans, by Navid.
Thank you. All right, let's see. Is it on? Okay. Oh, all right. Okay, so hi. Can you hear me? I'm Navid. I usually go under this avatar. If you don't know me, this is my face. And I'm in Melbourne, usually working a lot with Klima, and especially people at MIT who are developing the ocean component of Klima's new Earth system model. And I don't know if you've heard, Oceananigas is, this fluid dynamics library, which the ocean component of Klima's new Earth system model is based on. So, yeah. So I don't know if I need to, just to show you in turbulent flows in the ocean and generally in turbulence, the more we zoom in, the more we see. So here you see on the left an ocean simulation at a horizontal resolution of 1/12 of a degree, and on the right, 4 times more in each direction, 1/48 of a degree. All these details are very beautiful, first of all, but also they do matter for shaping up the big ocean circulation. So we need to resolve as much of these things as possible. At the moment, climate simulations, climate projections are done at 1 degree resolution. So imagine this 100 times less grid points. We are able with Oceananigans to reach pretty good simulated years per day at this sort of resolutions and reach climate projections now. We are envisioning climate projections that resolve all this turbulence. So I'll tell you a little bit about our philosophy and show you a little bit about Oceananigans. So when we're thinking of a new climate model, what do we need for this climate model to have? First of all, it needs to be fast. And especially because we'll have to run climate projections for many years in the future. We want to be able to run and rerun things to calibrate and find the best parameters possible for our parameterizations. So this parameter estimation, as it's called also. Definitely we want it to be fast, and also so that we can crank up the resolution as much as possible and resolve as many of these details as we can, so we don't need to parameterize them with terms that we don't even know. And the other thing we really want is to be flexible. We want to be able to be playing like Lego, as Milan was saying, be able to take out a piece of the code, put something else, take out the parameterization, put something else in, test things like that, and in order to, this would help us develop the parameterizations for the physics that we are not resolving. So, and we build Oceananigas, and it's quite fast. We we can get 10 simulated years per day at a resolution that resolves all these mesoscale eddies, all these circular features that you see here. Usually climate projections don't resolve them, and they have an ocean that looks like honey, like very laminar. And we have done that by utilizing hardware, like running on GPUs, writing the model from scratch with GPUs in mind, and using novel algorithms that enabled us to overlap communication and computation so that we can scale up, and we get almost perfect scaling up to 700 GPUs or whatnot. And then on top of that, on top of being fast, it's a really nice code, and it's like really user friendly. I don't know if you've ever seen a climate model. Milan was showing some in the beginning with these go-to statements and whatnot. Like usually we are there with state-of-the-art ocean models in Fortran, but we put a lot of effort in making an interface that is user friendly, so that people or users essentially write code like math or like LaTeX. And this is not just a comic code, it's an actual code that will run a simulation, a very simple one. But you can see here, for example, how I'm defining a new diagnostic. I'm just essentially writing it like LaTeX, okay? So Oceananigans, the library consists of three main parts. First of all, a lot of modules that are related with, finite volume calculus on discrete grids. So that involves defining the grid, defining fields, defining operators that act on these fields, derivatives, integrals, and parallel solvers and whatnot. Then there's another piece of modules that define how you read and write diagnostics, how you have these callbacks that you can call every now and again while you're running a simulation. And these two pieces of the library can be used, they have no physics yet. So you can use them either to build an ocean model or to build a sea ice model or to build whatever other fluids model you want. And a biogeochemistry, ocean biogeochemistry model, for example. And then we have like some physics there, some like actual fluid equations, and we can simulate from things that vary at the length scale of meters, so that's a full non-hydrostatic Boussinesq model, to the global ocean circulation, and use some hydrostatic free surface model, which is typically used for global ocean modeling. And I want to finish by showing you how this is also an actual code, with some there's some things missing here, but this code essentially will run if you fill in these little gaps. So I want to show you how you can, a user can build an Oceananigan simulation and then inject a neural network in it. So say we want to build a simulation and then we want to use a neural network to predict how do we force the U velocity at every time step. So what we are doing is we first of all build a grid, then we allocate some field that will be this forcing for the U velocity. We build a model, in this case this hydrostatic free surface model, and we provide this USGS as a forcing. We build then a simulation, which includes the model, all the equations, the diagnostics, we don't have them here, details about how the time stepping will be. And then we create a forcing function that will take this simulation as an input, and thus we'll have access to all the model variables and whatnot, and call a neural network, which I'm here using this LAX library, and then compute this forcing term as from this neural network. And then using a callback, as Milan was saying before, we can apply this neural network, apply this forcing at every however often we want. Here I'm doing it every time step. So it's as easy as that. So having a model that runs natively on GPUs and runs as Julia, we can incorporate neural networks like that and have like parameterizations taken to the next level. So with that, I'll let you go and hear questions.
Okay then, any questions for Oceananigans? I see one here.
Yeah, thanks. It was very interesting. I have a question in terms of, I mean, we all have the intuition that you increase the resolution, things get better in terms of error metrics probably.
Yep.
But can you quantify that compared to state-of-the-art ocean models, that are, not having the advantage of having such a high resolution? How much is this improvement in terms of, maybe representing the Atlantic meridional overturning circulation, for instance, or, whatever feature you pick, for instance, this one?
Yeah, well, whether we haven't done it in Oceananigans yet, because we are missing one little piece yet, which is sea ice, in order to have a full, what we say, OMIP simulation. It's like, but we are, we're hoping to have that by next February. But this type of questions that you are asking, like whether increasing the resolution and including less parameterizations and more actually resolving turbulence makes your solution closer to observations. It has been done by other models. So we are, so that's the idea. The idea also is that because one of the big parameterizations in ocean turbulence is the mesoscale parameterization. By going to a resolution that allows us to forget that parameterization, it reduces a lot of biases in the ocean. That's the hope, and we'll have climate projections without that parameterization. It will be amazing. But hold on to your chairs. Perhaps next year. Yeah.
Thanks a lot.
Okay then, if there is one last quick question. Otherwise, thanks again.
Oh.
And next up, we have a talk on sea ice physics by Scalar and Mukund.
Nope. Okay, we're gonna do this again. Well, I find it. Where did it go? Nope, I don't. Yep, okay, beautiful. Ah, thank you. Yay, all right, cool. Hi, everyone. Hope you're all having a good time in the session so far. So today we're going to talk to you about Subzero.jl. Subzero.jl, which is, a model that we are working on for fast and flexible sea ice physics. I am Skylar. This is Mukund, and we're really excited to share with you today. So to start off with, I want to give you a little bit of background on sort of two ideas of sea ice modeling. And sort of the first one is this general type that's used in global climate models. So that's sort of where we're envisioning the world as a grid scale, and within every grid, we have some sea ice, for example, in the Arctic, but we're envisioning the ice really as one big piece. And then within each grid cell, we're solving a set of equations to tell us the stress, the strain, or for example here, exactly how much ice is in that given area. But when we look at the satellite imagery and we look at some really key areas in the Arctic, that's not what sea ice looks like. So this is the Nares Strait. It's a really critical region for sea ice transport. And as you can see, all the ice in that region is made of lots of little pieces, these individual pieces of ice, and it doesn't look like that big sheet that we're seeing in climate models. So the question is, in these really critical regions, which for some other regions tend to be really key to Arctic melting, how important is this difference in representation for understanding dynamics? And so that's where Subzero comes in. So this is a discrete element model. So basically each individual piece of ice is represented as a polygon, and we model all their individual interactions and are able to have things like breakage and combination of different flows. And so then we have a native Julia implementation, and we're going to be talking today about how it's fast, flexible, and coupled. So I feel really lucky to be following both Milan and Naveed because they set me up really well. I don't even have to say why it needs to be fast. As Naveed touched on, a good model is a fast model because we're able to do more science. And so, this model actually started in MATLAB. And this has been a port and an improvement and a Julianization, we might call it, of the model to make it more usable. And so this bottom line, and we can see this is a log scale, we have the MATLAB speed, and then the dashed line is sort of where I was last year at JuliaCon, and then through some extensive work in the geometry ecosystem, since last year we've continued to push the speed up. And we're sort of on a final push of type stabilization to get it even faster. This is not working, right? Is the microphone not working? Okay. Oh, it is? Okay, cool. I think it's going in and out in my ears. Wonderful. And so we're really happy with that and really excited to see where we can continue going. But the other thing, as Milan and Naveed talked about, is really flexibility in Julia. And I was really inspired by both of their models when starting to work on this, especially as I got further into Julia. And so we're going to focus in sort of on a small example of this type of flexibility. And that basically is going to focus on flow scale breakage. And when ice is breaking, this sort of algorithm can change based on regime, or just maybe we're not exactly sure actually what the correct parameterizations are, so we need really easily interchangeable algorithms. But luckily, multiple dispatch is perfect for that. So similar to Sub-Zero and Speedy Weather, we have this setup where we have a simulation object, we have a model that holds everything, but additionally we have sort of these plug-and-play settings that the user can sort of set up a run with for all the different physical properties. So we're going to take a quick look at the fracture settings. And from our experience, setting up settings like this is really nice because it allows grouping of key parameters. So for example, how many time steps are we going to take in between fracture, or how many pieces do we want the flow to fracture into? And that really leads to ease of reuse of these discrete chunks. But in addition to that, we're actually starting to put algorithms into the settings. So for example, at what point exactly do we say a flow breaks? Each user might want to try something different as we try to, for example, match satellite imagery in a given region. And so basically, when two flows hit each other, the stress builds up between them. And the general way then to fracture is to look at, well, where exactly is this stress level on what's called the principal stress space? You can just imagine it's a coordinate system and the stress is a point. And typically we have some type of criteria, and if the stress is in the criteria, we don't fracture. If it's out, we do fracture. And so for example, someone might want a type of criteria that's called a Hibbeler yield curve. And so in this example, the stress is outside and the flow would break. But the cool thing is okay, we're dispatching off of this to say in this example we break, but we can also store the parameters needed for this type of calculation within the Hibbeler yield curve. So if you wanted a different type of breakage, so for example, Moore's cone, where the ice would not break because it's inside, we actually need a lot less parameters for that calculation, so we don't have to store them. So this sort of keeps users from having to find parameters you don't need and stops new users from having to scroll through a large input file of parameterizations where half of them might not even be used in a given simulation, reducing sort of confusion that can arise. And we use this idea in a lot of different places in the code, so not just when it breaks, but actually also the calculations for how we even build up stress in the flows, what type of walls we have on the simulation. And so with this, we hope to give the user, as Naveed and Milan pointed out, a lot of ability to play around with these really interesting dynamics that we don't actually know that much about. But another cool thing, and you can add your own, basically, is what I just said. Who knows what will come next?
Hey everyone. So my name is Mukund, and I've been involved a little bit with the development of Sub-Zero, mostly as a user. And what I'm thinking of using Sub-Zero for is essentially to explore different dynamics of sea ice. And here are some, for example, different mechanisms in which sea ice can break from satellite imagery. And sea ice can break in different ways, depending on the season, for example, the proximity to the coastline, the different types of forcings that are there. And we don't really understand exactly how to parameterize these at the moment. There's a very clear lack of understanding. And so here you can see examples where on the left-hand panel you have a lot of winds, which are creating shear into the sea ice pack and breaking it up in these kind of very linear features, which we call leads. And on the middle panel, you can see that it's a much more open space where collisions might arise between flows, and you can see them in imagery collide and break as a result of that. And on the right-hand panel, you see the effect of ocean turbulence, which is essentially shown by streaks of sea ice that take the shape of eddies. And superimposed onto this, we often have waves that can break the ice. So all of these three, you can imagine, will take different types of parameterizations to capture pretty well. So one of the case studies that I've started working on is the breakage of sea ice due to individual storms. So these storms essentially come up onto the ice and they displace it around, and they can cause breakage through these collision mechanisms, waves, as well as heating, which will make the ice a bit weaker. So in order to understand this coupled problem, we were able to essentially link up our sub-zero model with oceananigans and run some idealized simulations that I'll show here. So here, basically, we have a little patch of the ocean, which is only about 130 meters or so, kilometers or so in each direction. And essentially, the forcing is cyclonic, so it's a little simulated cyclone in a small patch. And we'll see these flows essentially move around in response to that. So you can see that this is a very idealized forcing, which pushes out these flows through something that we call Ekman transport. And you see that as these flows bump against each other, they start to break as well, some of these larger ones. And this is using one of the parameterizations that Skylar was talking about. But we can easily modify this and try to tune it to observations. Another thing that we notice in the simulations is the occurrence of waves in the surface of the ice. And this is something that we expect will also break the sea ice pack. And currently, we don't really have a parameterization for essentially capturing that process, but we're in the process of actually implementing that. So with this, I'll leave it to Skylar.
No, just to conclude, so we're using Sub-Zero to explore these finely grained sea ice dynamics and really focusing on, again, the powers that Julia gives us by being able to make it fast and flexible, and also thanks to the work of Oceananigans coupled. And so we're happy to take any questions. Thank you.
Okay. Oh, I see. Oh, I see so many questions actually. Okay, I can go to the others. Okay. Okay. Yeah.
Thanks for the talk. And my question is, well, I imagine that there is a lot of computational geometry that is involved in the development of this complicated model. So my question is, what do you use? Is it this geometry basics or meshes, or is it something that you developed, and what are your experiences?
Wow, are you a planted question? No. This morning, I actually gave a talk with Anshul and Raphael, and basically, when starting to build this, looking at the geometry ecosystem, we were really looking for something fully native Julia, and so that's sort of that increase in speed I was talking about. We're developing a new package, Geometry Ops, which I implemented the clipping for, and we're working on really improving the speed there, and we've seen a really big boost both in speed and also memory from using it, just in the way we've been able to clean up our workflow through Julia. And it actually uses a lot of really similar ideas with the plug and play algorithm. So not to pitch it too hard, but I guess go catch the talk on YouTube, and we would love any developers if you're interested. And I think that's also another interesting point. That's a really good thing for Sub-Zero, because when Geometry Ops improves, now we get this improvement without us having to continue to put in the work on the earth science side. So I would also make a plug for earth science people to consider contributing to more base packages for the sake of their model as well.
Super, thanks.
Okay, I don't think we have time for any more questions, sadly, but we can proceed for the next talk. Thank you again. Next up, we have Mauro. I guess it's 4 speakers, actually. So Mauro, right?
Yeah.
Or Annegret? Okay.
Yeah.
No. Okay.
It's
so
just me speaking.
Sorry.
It's just me speaking.
Okay, and it will tell us about sub-glacier flow modeling.
Yeah. Okay. Hello, everyone. So yeah, I'll be talking about subglacial water flow simulations on GPUs, and I guess as a upfront, we're still very much developing this model, so there's no users to be seen anywhere yet. So I will give them power as they come in. Okay, so that doesn't work. Okay, so subglacial what? So subglacial water flow occurs at the ice bed interface. It impacts ice dynamics, that's one of the important bits, so through the boundary conditions, but it's also other interesting features, like for instance, glacier lake outburst floods are important hazard. And so here on the left, you see a sketch of a glacier, and the blue lines indicate the water flows, possible water flows. And so here is a sketch of how this system may evolve during a season. So during winter there's little water, so there's a distributed flow predominantly, and then as more water is injected into the system, you get channels forming, which then take over most of the discharge, and then back again in autumn. And one of the models which can simulate this is the GLADS model, which I and others developed around 2010. And it simulates both the distributed system and the channelized system. And it calculates water pressure, which is one of the inputs into which you would then use to couple it to ice flow. So here is I guess the main equation. So it's an elliptic or a parabolic partial differential equation. So phi is this hydraulic potential. If that doesn't mean anything to you, then just take water pressure. And it's a diffusion equation, and it's a nonlinear diffusion equation, as you can see there in the term in the middle. It's a reaction equation, that's those V terms, and then there's some sources. So that's the main equation, so that's the only PDE. And we also solve some ODEs. The ODEs determine how the drainage space evolves, so how quickly, say, the distributed sheet opens up or closes down. All right, so the original implementation was using finite elements in MATLAB, and I guess one of the tricks we used was because these channel equations, they are not well posed in 2D, so they're only simulated in 1D on the edges of the mesh, but the distributed system is simulated everywhere. And then you get results something like this. So you get, this is for Gorner Glacier, an alpine glacier. Blue are the channels it develops. The contours are the contours of the hydraulic potential, and color is the water pressure. Okay, so we want to have now a modern GLADS in, on Julia and in GPUs, and why? Well, we know why, but so let's go to what we want. Yeah, so we want something which is hackable. I mean, the MATLAB code was actually pretty okay, I'd say, and it runs okay fast, but it's definitely showing its age. We want it to be differentiable, so we can eventually do inversions and sensitivity, and of course, we want good performance, up to probably about 4 orders of magnitude bigger domains than before, or meshes. So this is just a ticket for Julia. So now to the implementation. Now we use so before we had an unstructured grid, now we use a structured grid. Again, the channels only live on edges. So the spatial discretization is now staggered finite differences. The time discretization, we, at least for now, use just a backward Euler. The nonlinear solver is this pseudo-transient method, which is a damped relaxation method, which works really well on the GPU. At least, well, that's when it works well. It actually doesn't work so well for this model, so that's one of the reasons why it's still work in progress. And we use a GPU, CPU agnostic coding using this parallel stencil framework. And so this is like a code snippet of how one of the compute kernels would look like. So that's the kind of inner compute, which we would compute at each grid cells, which gets them mapped either on the CPU and kind of just a for loop, and then on GPU with whatever the CUDA stuff does. And so the macro at the top is the finite difference. Actually, the finite difference, I won't be able to scroll. The finite difference is sadly just off screen, but yeah, it's just the difference of phi at one grid cell versus the other. And then there's the bulk of it is this, what starts with these parallel indices. So that's one of the macros from parallel stencils, which provides some, well, basically indexing functionality. And it takes a bunch of stuff, and then it calculates this flux. So so here is this nonlinear diffusion diffusivity calculated, and then the flux is calculated. Well, it's a kind of an update. So this is this pseudo-transient method, which relaxes the flux until essentially the definition, the mathematical definition of the flux equals to 0. This bit here. Yeah, and I mean there's a bunch more kernels, and you loop through them to iterate. Well, both the nonlinear iteration with this pseudo-transient method, and then the iterations over time to step this forward in time. So this is a example of some first results we're producing. So this is a synthetic setup of a ice sheet margin-like topography. So ice and water flow is from the right to the left. And at the top you see these channels, the blue things which form. So this is a run into a steady state under steady forcing. And the arrows indicate the directions of water flow in the sheet. So you see as the water gets drawn towards the channels, so quite similar to subaerial drainage, where rivers collect water from smaller rivers from overland flow. And at the bottom you see essentially the water pressure. So the water pressure is, well, this is effective pressure, which is ice pressure minus water pressure. And yeah, the water pressure is lower in the channels, so that's why they draw in the water from the sides. Here's another example, but let's jump over that. And so doing the outlook, so we need to fix the convergence issues we have at the moment. So the plan is to use a conjugate gradient method, and we're pretty confident that that should work, and that should also run fast on the GPU. So that's definitely the next step. I want to look into resolving channels. So at the moment they only live on these edges because the equations are ill-posed in 2D, but we can add some extra terms to make them well-posed, but then you need really high resolution to resolve those meter scale type channels. We want to couple it to our ice flow model, the fast ice model, which you may have seen a presentation about 2 days ago. And yeah, we want to work towards inversions. And yeah, hopefully with a bit of luck, we'll soon have PhD postdocs openings for working on this. And then just a side note, there's other kind of geo-related package I have, which is called Where the Water Flows. This is a simple D8 routing package here applied to a glacial setting, but it works also for subaerial settings. So if you want to route some water around your topographies, then that's where you can go and look. And yeah, with that, thank you.
Okay, then. Are there any questions? I see one over there.
Can you guess what my question will be?
No idea.
Why implicit Euler? Also, why pseudo-transient? Because pseudo-transient's one that kind of baffles me, because it's always it's like a non-adaptive line search method, and so it tends to always be slower than adapting line searches. So I'm kind of really curious about that one, but also why the backwards or the implicit Euler choice as well.
Yeah. Okay. So I mean, the backward Euler choice is just a simple one, and there's probably a good use to use adaptive time stepping eventually, and so on. In particular, if you have kind of seasonal forcings, and then you definitely want to have adaptive time steps, and probably something slightly higher order than backward Euler. But yeah, I guess I should have put that in the outlook as well. The pseudo-transient I guess, is our go-to method in the sense that it's easy and it's well easy to implement to run well on GPUs because it's kind of a really local method, so you don't need any global reductions. But I mean, in this case, it doesn't work well, and the conjugate gradient should address the reiterations you just stated, and so we'll see how that works in the future.
Any reason to not try trust region methods or other line search methods?
I guess we could look into those as well. I hope we don't have to. I hope that conjugate gradient will just work.
Okay. Any other questions? Okay. This is a long play.
Yeah, thanks for the talk. It was very interesting.
Yeah.
I have a question with respect to the inversion, because your main observable in that case is just the surface velocity of ice, I guess? Or do you have additional observables that you can tune your hydrology model to?
Yeah, I mean, yeah, that's one of the issues. The system is hard to observe. So, as you said, probably one of the best strategies is to invert kind of a coupled ice flow hydrology model, and then you can use surface velocities. But other observations which potentially useful are kind of in situ experiments, like tracer experiments or proglacial discharge measurements. Yeah, but at a large scale, probably only surface flow speed measurements from satellites are feasible.
Because for that, I mean, there's kind of a complication because you also don't know the basal friction properties at the bed of the ice, right? So you kind of have this difficulty to disentangle two parameters. It's kind of A times B multiplied with, you know, whatever state that you have, and you can only really get the combined effect of both, right? So I don't know, if you have thoughts on that, I'd be very curious to hear them, how to disentangle that as much as possible. More data, I guess, but...
Yeah, I think one of the potential ways is if you look in time. So maybe you think that the kind of fundamental parameters in your sliding load, they might be constant over time, but then you have a seasonal cycle and you have a seasonal signal in velocity, and that seasonal signal will come from changes in the hydrology, and so then that might be one way of disentangling it. But I think it'll be difficult.
Sounds good. Thanks.
Okay. Thank you again. And next up, next up we have Jordi with the SciML for glacier evolution.
The link is on Slack. There you go. Awesome. Thank you. Awesome. Thanks a lot. Hi everyone. So yeah, I'm Jordi. I'm a researcher in Grenoble, in the University Grenoble Alps, and I'm very happy to speak after these really cool models and talks. And I will be presenting mostly Odin, which is a project, a library, a large-scale glacier model that we've been developing the last 3 years. It's pretty much work in progress compared to very solid results I've seen so far. And I will mostly be focusing on two aspects of the use of Julia. First of all, multi-language interoperability, and also how to leverage the SciML ecosystem for geoscientific modeling. So first of all, when I mean a glacier model, what is it? So as you can see in this animation, there's a lot of things going on glaciers. First of all, from my opinion, they are one of the coolest systems on Earth. And in order to simulate them, first of all, we need observations. So we have two main types of observations. The first one is field work. We go to the glacier and we normally have point observations, high quality data, but super sparse. And the other main type of observation is satellite remote sensing. So in the recent decades, there's a huge increase in satellite remote sensing, and they have a very good spatial coverage. And it's this that is mostly revolutionizing a bit the way we can model glaciers. But then, of course, in terms of modeling, we need to model two main things. So the first thing is like ice and atmosphere interactions, and then ice-ocean interactions. So this mainly determines like the gain or loss of mass of the system. And the second one, which is pretty evident from this animation, is the ice flow dynamics. So basically, as a bit like Mauro said, like how the ice deforms or slides at its bed. But then, in this context, so and also in the wider context of geoscientific modeling, why is Julia so interesting? So as I showed you here, we always have these two ingredients, data and then some models. So these two elements for geoscientific model have very specific characteristics. On the one hand, data is always like spatiotemporal, highly sparse, and very noisy. And this is both the case from satellite remote sensing and in situ data. And then in terms of models, like these models, they need to work at different spatiotemporal scales. We need to simulate maybe 1 day to multiple centuries. And sometimes if we have to work at the scale of the globe and then resolve something as small as maybe like cloud microphysics, we will not explicitly resolve those, so we'll use empirical parameterizations. And then importantly, since on Earth everything is connected, we need models that can be easily coupled among them, especially, for example, to simulate the interactions between the ocean and the atmosphere. So why is Julia so interesting here? Because from my point of view, two main ingredients. The first one is differentiable programming. If we can compute the gradients of our model, then we can easily assimilate and digest all of those huge amounts of data, and then we can perform very cool like inversions or optimizations. And the second ingredient is this multi-language interpretability, because as we have seen here, we really need to couple these models between them. And unfortunately, not all models are coded in Julia, so we need to talk to the outer world, and Julia is very good at this. So what is Odin? So in a nutshell, basically we're building a scientific machine learning glacier model. And we're building a modeling framework which intends, of course, to assimilate all these heterogeneous Earth data for glaciers coming from satellite remote sensing, in situ data, and also climate models. And the idea is, of course, to use these differentiable programming capabilities to assimilate these observations in the modeling framework. And we have one main scientific objective in mind, which is to discover new laws. And by laws, I mean mostly parameterizations and empirical laws. And the thing that we're really heavily trying to investigate here is the use of universal differential equations. And by this, I mean basically to use partial differential equations to solve them with traditional numerical solvers and to embed a regressor, for example, a neural network, to parameterize a subpart of that equation, normally to capture some missing physics or just to explore like some unresolved processes. So the main goal here is basically to parameterize key physical processes of glaciers, with the goal, of course, to improve these models and then to perform glacier evolution predictions under different scenarios of climate change in order to understand how they will evolve in the future. This modeling framework is purely coded in Julia, but an important piece here is that like we heavily rely on two Python packages, and for this we rely on PyCol. And these two packages are, first of all, the Open Global Glacier Model, which is a very big community-based model in Python, which we purely use to retrieve the initial conditions, so all the topographical and the climate data for our glaciers. And then we use X-array to process and all these large data sets. So just a quick overview of Odin. This is a publication that we published last year where we presented like a synthetic study to understand the properties of UDEs with this type of partial differential equations. So we use this Python package to retrieve all the initial conditions of our glacier, and then we build a universal differential equation using the SciML ecosystem. We have this partial differential equation describing the flow of ice, and then we embed a neural network in it, like describing a physical law. For example, here it was the changes in the viscosity of the ice. And then we run this forward with a numerical solver until we hit some observations. We compute an error in the loss, and then we use this to optimize the parameters of the neural network like iteratively until we fit the observations. So if you want like the details, you can check the QR code there. So these 3 years were not a walk in the park. So we learned a lot of lessons, some good and some like harder. The first takeaway for me would be like that UDEs right now, for small problems, they work pretty well. Like by small problems, I mean like simple code architectures and a reduced number of ODEs. So this, we can already tackle very cool like research questions with that. But with the type of big problems that we're tackling here, it's still pretty rough, and mostly because of the common thread that everyone is mentioning, enzyme. We need good AD support for these big problems. It's coming, but it's still not there. So from this standpoint, what are the perspectives on where we're going? So first of all, we're working towards a 1.0 release, and by 1.0, I don't mean like as mature as maybe the previous models that we see. It's just like we completely refactored the architecture and the API, like splitting it in 4 packages, and we're also building towards compatibility with enzyme. And we're mainly developing the model with 2 objectives in mind. The first one is this, inferring parameterizations of these key processes of glaciers from these sparse observations of glaciers and any Earth observation that can be interesting here. And of course, the scientific aspect here is we want to assess the impact of glacier retreat under climate change on water resources in vulnerable regions such as the Andes or in high mountain Asia. So if this is of interest to you, first of all, please check out the GitHub repository. We welcome more developers in the earth sciences aspects or in the same aspects. And also I would like to advertise that I have an open postdoc position for 2 years to work with me in Grenoble in the beautiful French Alps. So if you like SciML and earth sciences or glaciers, you will be able to visit them. They're here, and also work on them on Julia. And the second advertisement is we recently released a review paper on archive on differentiable programming for differential equations. So if you like this topic, please check it out, because Facu did an amazing job, and it's 50 pages long, so it covers a lot of the details. So with this, I thank you for your attention, and I'm happy to take questions.
Okay. Who has any questions? Can get to one here. Okay.
I'm just curious what you mentioned your model is not compatible with automatic differentiation yet?
No, it is compatible. It's just that in this paper that we published, we used reverse diff, which worked well, but it's just because we had a simple model architecture to make it work. And now we upscale it to a bit like the same philosophy, modular with nested structs and so on. And when we moved to this more complex architecture, it completely broke. So now we're kind of aiming to work with enzyme in order to have this full compatibility with all these features.
Okay, but it's not just a scale question. It's actually something different in the model when you
I'm sorry?
I don't quite understand what is causing it not to be compatible with the automatic differentiation anymore.
I mean, it's not that it's not compatible with automatic differentiation. It's not compatible with some libraries, and I mean, there's many things that don't work with enzyme, but it's mostly garbage collector and PyCal compatibility. Chris knows all the details.
Okay, thank you.
So last question, and then we go to the break. We are already kind of over time, but should be fine.
Yeah, well, I was just going to comment on what's going on with their AD issue, right? So the AD issue that they're having is mostly edge cases in the garbage collector because, for example, when you read in the glaciers, you end up reading them as X-arrays that are owned by Python, but then are worked on by enzyme. And so you need to make sure that the garbage collector from enzyme knows how to deal with this interlanguage stuff and does not free things that live in another language. These are different edge cases in the garbage collector that enzyme had not handled before. And so we are working with Billy to make sure that we can handle these cases. There's another case with timeroutputs.jl, which because that uses a direct global reference and such. So it's nothing to do with the numerical codes at this point. Like the numerical stuff is all differentiating just fine. It's just all this other, I use PyCal plus this, plus this, plus this, plus this, and I piece it together. These are the things that are now in the realm of making enzyme mature and robust for those aspects.
Okay, so thank you, Jordi. And thanks to all the speakers for this first half. Again, we are kind of late, but we can take 5 for a quick break and rendezvous at 3:45, right? Yeah? Okay. Yeah, okay. Yeah, 5 minutes, yeah. Next is you, right?
You are giving the chance to anyone, for everyone to go.
Yeah, take a quick coffee, very quick coffee.
This is Jordi's, right?
No, that's Skylar's actually.
Skylar, okay.
Skylar, your laptop?
You don't need it anymore?
So this is like, for me, this is like this only initial condition. So I was like, I'm not going to differentiate for that, so I should be out of it. So, but then it backfired. But it's just like that I know the XML so IPI so well that it was just like so easy. What about like, but you know, it was very easy. When you're running a regional press, I know, but like I just need like yeah, that's the thing. I would not be able to like there's a functional dependency that will never be able to like really efficiently. Basically, instead of building yet another data model from scratch, there's this community model. They do a lot of things well. So like all the performance, it's basically it's cool to the point that there's a big like nature released on the New York these guys take the time to like process it. I mean, I'm using the same type of like interface that they use for Glacier, so I can have every like published data set available on Odin with zero effort. So I have very strong reasons to stick to their like it's almost a community standard. Yes, but the problem is like we don't work with files. We work on a glacier-centric setup where we simulate each glacier independently. So we have like the polygon with the glacier outline and the rasters for each glacier, and there's an adaptive mesh as well, which is like meaning the horizontal resolution is adaptive depending on the size of the glacier. So there's a lot of reasons to adopt. Anyway, it's like if you use a so if I move to the rasters, I could drop one byte of dependency, but I would still be reliable. The only thing is also like I want to move people. You know, it would be good to feel like fidgeting and you can have the other one, the triangular one.
My installation of the
But it's mostly like the initialization because it's a bit like yeah. There's the interfacing is a bit like
if I lose internet on
and if you have like this
airplane, right, while I'm trying to initialize it, then it'll be like, oh, didn't show itself.
But this is on the Python side. It's like so basically you're pulling like very big files, and if that is like interrupted at some point, it will completely cover the files. Yeah. But it's not really things for open global version. I told you to go to the toilet because then it's me. I don't know. I'm sorry.
You know, I remember I was with John. It was just very like we use the package.
Yeah. So it's like, you know, it enzyme is supposed to be on your stuff. That's most likely when you're around with like all that stuff. You know, these things that are hitting over memory or memory that is
next year. All right, so to reach out. Yeah.
I'm working with Lily to make it more robust for all those containers, but I mean, those are not, you know, those are not the test cases that we have. So it's just in the last one. It's essentially like all of the areas that are isolated, none of them, you know, like neural networks and everything all work now, and everyone's all happy with those. It's just
You're like being
managed somewhere else.
I don't know.
Another thing is like progress tools.
Yeah, well, reach out because there's not many of them. Yes.
But normally it's like,
geography and
one of these species.
Yeah. So, well, now they there. I don't know if you know which building are you using. So there's like
Testing, testing, no.
Near physics.
Never be late to your own job. We'll be right for you. Should I get you one?
Maybe. I mean, you already know the presentation, so.
Why is my name not on there?
Oh, it will be.
Okay.
It will be. Was my name on yours?
No, did you work on it?
Yes.
What?
All the visualizations. Yeah. I think this one doesn't work.
Hello, hello.
Okay. This one. Hi, hi. Hello, hello. Hi, hi.
Sorry to interrupt, but we need to move on. We are behind schedule. Well, thanks a lot for all the super interesting talks. We're going to move on with the second block, and the next speaker is Lázaro, who will talk about strategies to integrate data and biogeochemical models.
Yeah, thanks a lot. I mean, thanks for staying. Yeah. So today I want to talk about our experience with Julia. So I will mainly show some lessons learned that we should think twice before moving forward. And by we, I mean a bunch of people at my institute that are part of the group. And yes, what is the question that we want to answer, or what are the topics that we are interested in? So basically, we focus not on ice, not anymore. We focus on water and carbon. So, and what I mean by that is that we use physical models to simulate these processes, such as photosynthesis, carbon allocation, wood, litter, root. So all these processes that are happening in plants, we study them via equations. So, and these equations will output some quantities that can be measured afterwards. So these measurements that we take at the end are like evapotranspiration, carbon rates, and the vegetation health, like NDVI. So this we call targets. So once you have your models, what you want to have at the end is a comparison between the model output and these observations that you will measure. So your equations usually have parameters. So, and you want to parameterize this, okay? You want to optimize these parameters. Why? Because these parameters usually are site dependent, okay? And when I say sites, so the sites are the observations. In this case, we are using FlowSNEC sites around the globe, which collect all this data, okay? So this is the data that we want to integrate into our models. More than that, so we will use remote sensing data as well to simulate all these processes. So this data, which I am calling forcing, is time dependent. So we have years and years of data for all these variables. And for parameters, I have static data. So this data is the one that I will use later on to optimize these parameters. So my goal is twofold. So I want first to do optimizations per site. So that means that I will optimize these parameters in each location individually. In a sense, I will be overfitting, right? So once I optimize parameters on one site, I cannot transfer those values to other sites. So the goal that we endeavor here with Julia was to build a framework able to specialize for parameters that can be retrieved in a spatial manner, okay? So in this plot, I show how this data looks like. So the black dots are the observations that you will usually have, and the blue line is the output from the simulation in this site. And the red line, of course, is the result that we get from this model that can specialize in the spatial domain. So, but how do we solve this problem? Well, we learn Julia. So, but when we learn Julia, we need to make some decisions on the model and design. And you will see some resemblance here to Speedy Weather. Apparently, we converge on the ideas in every model framework. So for us, it consists of 4 elements plus 1. So at the end, I will mention what is this one. So first, we define a model, and we try the definition of this model to be as simple as possible for users as well as for scientists. So we start with the definition of this model in our land ecosystem, okay? And then just to say, for this approach, for this process, for this physics process, I can define my own model. In this case, I call it my example. And usually when you have these kind of models, you will have a parameter, right? But from physics or from observations, you usually have a given value. So what we do in this definition, we say, I have some default values, but then I can attach the units for that. I can put a short description, and I can also encode the bounds, okay? So we wanted to have something simple to read, so just not like equations, but more like natural language, okay? So this is the best we could come up with it. Then forcing, so each one of these models will have a forcing. So the forcing means that you have some input variables for this model, and these ones can be constant or can be arrays as well. LAN is also a collection of named tuples. I mean, as you can see, the syntax is named tuples. So you have your model, input is forcing, which is a named tuple. LAN is also a named tuple, but this named tuple can also contain named tuples, okay? So basically, you have your model, your forcing, and your bucket. We call our bucket LAN because we will put everything in there. So once you do a computation, everything will go into LAN. And helpers is something generic that will be shared across components. Yeah. And the plus 1 is basically compute. So compute is basically you define your model, and once you define your model, you have your forcing, your LAN. You can say, okay, I need this variable from this one and from that one, like diagnostics, fluxes, and then you do some calculation, like calculate variables, like a new value for your variable, and then you say now, pack that new value into my diagnostics field, or my pools, or my fluxes, and that's it. So you want to create a new physical model approach, you do these steps, and then you can plug in and play with this anywhere in your workflow. And yeah, one of the lessons that we learned the hard way is, yeah, we should aim from the beginning for 0 allocations. And types. Like all the types need to be known. So for our framework, we make sure that we have always 0 allocations and all the types are known. And once you have this, you can have all your models run in sequence. So you usually pass a tuple of models in the right sequence, and then you run them all. And because everything is 0 allocating, it's quite cool. So what do we want with this? So we can do automatic differentiation, and we are able to construct a complete workflow to optimize our parameters in space. So basically, we have the static variables. In this case, our new model for these parameters is a neural network, which will output new parameters. You will have your forcing. You will have your terrestrial ecosystem model, the collection of all models. You have your predictions. Then you calculate the loss. But because you can do AD, you can calculate gradients. You use those gradients. You multiply by the Jacobian. And then you can update the weights of the neural network. And then you repeat and repeat and repeat and optimize. So in conclusion, we have these lessons here learned so that we are able to optimize these parameters in space. So I would like to love and hear your thoughts on this. And please don't hesitate to ask or talk to me after this. Thank you a lot.
Thanks, Lathrop.
Yep.
We have time for a very quick question.
Cool.
I have a question. So maybe can you get back to the slide of the neural network that you said? So what is the result, or what do you want to put inside the neural network itself? Just the data, or?
So the input to the neural network is data, yes, are all these static variables that I mentioned at the beginning.
And the output is?
In the output, it will be new model parameters. So it will be a collection of parameters that go into your equations. Okay?
Okay. And
so because I want to optimize for all of them at the same time. So when I do these static variables, I'm passing a matrix that will contain values for each site. Okay?
Okay.
So it's a batch of observations.
Okay, so you just want to find the parameter of that site?
Of that batch of sites, yes.
Okay, okay. That's clear. Okay.
Cool. You're next.
Cool. So moving on. Applause for Lazar, please.
Thank you.
So next speaker is Tim, who will be talking about species distribution models.
Yeah, let's see if this works. With an honorable mention for RAF. We were on a train, a lot of trains through Europe, trying to minimize our CO2 emissions. Then I said, if we're on a train for 3 days anyway, from from Malaga to Copenhagen, we might as well write a package. And here we are with half a package and a pitch. 3/4. Wow. Okay, not touching anything anymore. Yeah, happy to be here, also a bit humbled. I'm an ecologist, a biologist, doing species distribution modeling, and it's much, much simpler on the surface, I think, than all of these other models. But maybe I'll try to convince you also that it's the most important types of models you've never heard of. So what are these species distribution models? Basically, the idea is we want to know where a species can live. And the way we do it is we have some observations of species, so it's the points in this slide. And we try to correlate where we find a species with often environmental variables or things like slope or the soil. And that way we can just build a model and say in what types of environments do we find this species. And of course, one very important application of this is climate change research, where we want to know not only where a species is found today, but where it's likely to be found in the future. So if you've heard that species are going extinct with climate change, or diseases are coming to new places, or invasive species are invading, these are the types of models we use actually for that. This is how we know. So I wanted to explain this to a math professor, and then he said, isn't that just another word for regression? And maybe some of you are thinking that, and I mean, in a way it is. We are regressing something. But it's also a big, big field of research. And over time, there are common standards, reoccurring problems like spatial bias. There's the same data sources that people are using again and again. So it makes sense to, build an ecosystem around this. We're just checking like this one foundational paper, methods paper. It's close to 20,000 citations. So it's really this huge field of research. And today, so these 20,000 citations, what are people, using to run these species distribution models? That's R. I mean, ecologists, they all use R. There are dozens of SDM packages in R. There are multiple that run entire workflows. And I mean, these work, right? Like, because there are so many people working in R, entire labs developing these things, they're very, very complete. Like every single thing you can think of, someone's implemented it. There's all these tutorials floating around, which makes it, super easy to start. And maybe it's good to say that, the average practitioner of SDMs, they're not in this room, right? They're not at this conference. They're first ecologists and second programmers. And so you run into these, big problems with R packages that no one is solving. Like, they're incredibly slow. Like, people will be running these for a month on a cluster, even though they're just running some pretty simple models, and the syntax is not great, and the customizability is very bad for a lot of these tools. So we're trying to do it in Julia, and already when we started in the train on our way to Copenhagen, we said, okay, we don't just want a package. Like, as much as possible, we should make this possible by, committing to existing packages like rasters, and we rely a lot on MLJ, the MLJ ecosystem, to make this work. And then we make this one package that, the ecologists can understand, and then we'll build on both MLJ and rasters and kind of bring it all together and make it as easy as possible to make SDMs. So just let's do an SDM. I chose an Australian species because Australia is nice and isolated. Eucalyptus regnans. It's the tallest flowering plant in the world, and it's actually kind of threatened, so it's not totally irrelevant to want to know. And now we'll just do a quick workflow and see if we can make an SDM for this species. So the first thing we want is some environmental data. So I use rasters, and I use raster data sources, and these are easy to just download from the web. Now I'm just using temperature and precipitation as a covariate, so this is what it looks like in Australia. Most of it's dry, some of it's wet, most of it's warm, some of it's cold. That's Australia, right? And then the next thing is occurrence data. So here we're using GBIF. It's this big collection of occurrence data. People took a picture of a tree and uploaded it with their location. We're downloading all of those observations, and then we're doing this very typical thing, which is spatial thinning. So, if you found one tree of a species, probably there's another one right next to it and another one right next to it. And we don't want the entire forest in the model. So with the thin 5,000, we're just saying we're removing random points so that all of them are at least 5 kilometers away from each other. It's one of these, classic things that people just started doing because it works. And then we need something to regress against. We can't just have presence points. So there's also a classic thing. We just say we have our presence points, and then we sample random background points from Australia. So we're teaching our models to know the difference between a location where we found this eucalyptus species and a random point in all of Australia. And again, this is what it looks like. In the gray, we have random points. And in red, we have places where our eucalyptus species was found. And now is where the species distribution models package comes in. We just make some data objects where we already do our cross-validation and put all of the presence and background data together in one object. And it prints some useful information like how many folds we have and what kind of predictor variables, so we can check that this all works. Then we need some models. And one very, very common thing to do with these in this discipline is to take multiple models, fit all of them, and then take the average at the end. So here we're using MLJ, we're using a Maxent model, which is very popular, a boosted regression model, and just a GLM. And we fit the entire thing by just calling SDM on the data object we just made and the name topper with the models. And then it just fits all of them. I mean, that's MLJ, just calls MLJ in a loop and fits all of them. Of course, we want to know if this works. So again, we just called SDM.evaluate on the model, and it tells you for the train and the test data the performance of the individual models and of the entire ensemble. In this case, it's like 0.98 AUC or something. It's a very easy species I chose. And then we predict. Again, it's just SDM.predict. We just want to reduce by taking the mean of all of them, and then this is the map we get. I mean, not so surprising, given that this is where the species lives. So in the south over here is where our models predict that the climate is suitable for the species to survive. And if we want to do, I didn't do it now, but if we want to do for the, for the future, a climate change scenario, we just predict to a different set of climate predictors for the future. And then there's a few cool things, like we want to kind of know why, in many cases, the model predicts the way it does. So we can explain and call Shapley values, and we see that, for example here, this is interactive, not right now, but it can be interactive. The colder it is, the model favors cold environments. Yeah. So this all kind of works. But we need to get all those R people, the 20,000 of them, to come over to Julia and start using this. So what do we need for this? Well, I think this package is, hopefully makes it easy enough for them, but it's still early stage. It needs to be more complete and more documented. We need all those pros that R has, right? And then we also need the cons to not be there in Julia. We have all these models in MLJ, and we can interface with them pretty easily. We have these raster packages, which are great. But I think what we need is, tutorials across the packages to make people understand this. Also people who aren't, first coders, but first ecologists, then coders, programmers. We need all the tools in Julia, like GAMs are something we don't have in Julia right now, and it's kind of a must for this kind of modeling. And yeah, we've been talking about that in the geo ecosystem, the syntax sometimes isn't as intuitive as it could be. So I think it's also something we might need. That's it. Thank you.
Are there any questions?
First, a comment to your last point about the tutorial. So tomorrow is the hackathon, so I'll be happy to sit down with whoever's want to work on tutorials on the Julia Geo ecosystem. And then a question, could we inverse this? So say we have a distribution of species and predict the climate from that?
I guess. I don't know. It's not something ecologists do, right? Ecologists are mostly interested in the other way around.
So what makes this unique to ecology? There's something in the species distribution, like a distance function or something, that makes this unique to species?
No, it's just another word for regression, right? I mean, you can see the math professor classes. You have them on right now, and then it's just another regression. Again, I think it's like, it's a field that has developed. And so people have kind of started agreeing on that the best way to do this is, for example, to fit 5 models and take the average and not just fit 1 model, right? So there's these kind of common tools, common models that you could use in all kinds of problems. But people have found out or agreed on that we should use them for this model. So, but no, I don't think there's anything, fundamental about, fundamentally different. No.
Okay, I'll make it very fast. It was very interesting. I have no idea about the topic, and my question is, there's actually a time component in the problem, right? I mean, if I start cutting trees and then I stop, the climatology didn't change, but I did a perturbation that needs some time to recover. Is that something your package can embed at some point? Is that something that people don't do in species distribution modeling?
I mean, people add predictive variables like a human perturbation index or these kind of things to have human influence. But it builds on this biological theory that for every species there's a set, there's a n-dimensional environmental space where it can live. And that's the kind of the space we're trying to find with all these models, right? So you're not always predicting where you find it, but where it can be found or where it can live, right? So that's the kind of theoretical.
Okay, another round of applause, please. So we're moving on. Next speaker is Lisa, who will be talking about how climate economics domain experts use an embedded DSL.
My models are even simpler. So we're going like low to, we're going up as we get tired. They get simpler. There's no math in this entire presentation. There is math in the model, but I'm not going to show it. Okay. I'm Lisa. I just graduated from UC Berkeley. I'm going to be presenting information about a paper that I published with Sarah Chasins and David Antoff at Berkeley, and next year I will be a postdoc at Stanford. So hopefully keep working on this stuff and always happy to chat. So I'm going to be presenting the findings from a recent paper that actually examined the usability of a package that I and my advisor built. So this is sort of giving power to the user by physically watching what the user does and then trying to infer what would be helpful to them and where their pain points were, which is like a really fascinating experiment to do. I highly recommend it. Super time consuming, but really interesting. Okay, so I'm going to be talking about Mimi.jl. This is an embedded domain-specific language or package. I'm going to be saying EDSL because that's the term we were using in the publication, but you can think of it as a package too. Same thing in this case. For integrated assessment models. These are like cornerstone models in the climate economics field, and very broadly, they calculate what the economic impacts of climate change will be, and then produce values that are meant to be really useful to policymakers and regulatory agencies. And they're used very widely, and they couple a lot of systems together. So they couple climate models, like the ones we've been talking about, generally emulators that are emulating the more complicated behavior of models that take months to run, with socioeconomic projections, and then also with models of the economy. And they are mostly used by non-programmers, right? So these are not people who are programmers initially. Quick features, similar to a couple of the talks, we're focused on this being very extensible and modular in this sort of like Lego-like approach. And we really try hard to match our syntax and structure to the mental mapping of our domain experts, who are often not coders again, at least not coders first, so it's helpful to sort of like match to the domain language. Some of our models are actually built as packages, so we have to deal with package management and package development often, a design decision that's had some unintended consequences, but here we are. In a very Julia way, we use custom types and multiple dispatch quite a bit, and perhaps more controversially and problematically, we do depend pretty heavily on macros, which was not a decision I made. I hope my advisor's not watching this talk. Okay, so just to drive this point home, Mimi matters. So on the left, we've got, I think, well over 20 or 30 models on this platform already. These are built and used and developed by research organizations in the United States and beyond. They're also used by NGOs and the government. And then also in like recent interdisciplinary publications in journals like Nature, and that particular publication was like a collaborative effort between researchers, policymakers, and an NGO. And then also, this package now underpins the open source code for recent regulatory action within the United States, and also some in Germany. That is the word for the German Environmental Protection Agency. I have 3 German advisors, and they ruthlessly mock me when I try to say that word, so I'm not going to. But is there anyone German here? There we go. He said it. Someday I'll be brave enough, but I'm not now. So to drive home the motivation just a little bit more. So there's evidence that suggests that there's an opportunity for language designers to improve the user experience via better understanding of the user needs, these end user needs of an embedded domain-specific language. So what I mean there is there's a lot of potential benefits, right? As a designer, we don't have to write a new general purpose language. We can just add a layer of constructs and syntax on top of a general purpose language, use everything that's already built, use all those packages, super attractive. For users, you'd think they can do something pretty similar, right? They can depend on this whole ecosystem, package management, etc. But some of the literature seems to suggest that for designers, yes, super low effort, really useful. We like using this like embedded approach. But for users, it's actually a more mixed bag. And some studies have shown that for end user effort and debugging and understandability, it's actually not really living up to its potential. So the goal of this study was to understand why that gap exists and try to work on it a little bit. So again, we're trying to understand what kind of programming challenges domain experts face, and then also which ones are specifically because it's an embedded DSL. So we just kind of honed in a little bit more on that property and these relationships between the embedded domain-specific language and the host itself. And happy to talk more about the methods later, but very broadly, this was a user study with domain experts. So our experts came from NGOs, academia, and the federal government. All of them were already using the package. And the method basically was me sitting on Zoom on mute, watching these people use the package in the way they use it. So there's no quantitative results here. We're not like timing anything. I just wanted to understand what they were doing and where their pain points were. And very rarely interrupted unless I had like no idea what was going on. But I did ask them to give me sort of a stream of consciousness. And then using some kind of human-computer interaction theory, thematic analysis, we built up theories about their pain points, good and bad. And we focused on the bad, but there was a lot of good. But yeah. So second part, we have 5 key categories of findings and then related design considerations. And those 5 groups are listed here and they're in the paper. There's not even nearly enough time to go through all of these. So I'm just gonna give like a little teaser of examples of the top 2. And then I'm happy to talk about more or also just point you to the paper if you're interested in some of the specifics here. There's some on tutorials and kind of whatever your interest lies, there might be nuggets of interest. But I'm going to focus on those 2 top ones. So the first one is that errors expressed in host language concepts may slow down and confuse users, especially for those new to the host language. And this was sort of like empirical backing for existing claims in the literature, so this has been talked about quite a bit, but we found the same corroborated, so that was interesting. What do I mean by that? Well, this quote was fun. The Mimi API errors in a similar way to the way Julia errors, such that the error messages for someone who isn't savvy in all the types, like abstract bool, can be a little bit like Morse code sometimes. So this was a user who wasn't super used to Julia, used to R, not used to types, etc. And so maybe somewhat unsurprisingly, a participant's ability to debug their code depends on them understanding error messages. And when those error messages are expressed in the host language that they might not know very well instead of their domain language, it can be quite hard for them. So on one hand, this might be par for the course, right? Like, you're going to write an EDSL in a host language. Your users are going to have to learn a bit about the host language. And that is what it is, and I think that's fair. But on the other hand, we did find that some of the design considerations and the design choices we made it more likely for them to hit certain classes of Julia errors. For example, we use macros, so they started hitting errors that are common when a macro parsing or something doesn't really work out like you expect. Newsflash, those are really, really confusing errors. So our kind of learned lesson here is that while people might need to learn a bit of Julia, we as designers can sort of at least quarter off the types of errors they're likely to get, and we can design, or we can just really add that to tutorials and really help users say, okay, if you see this type of error, this is where you can look. And then one more example, and this somewhat contradicted the literature. So the literature on embedded DSLs is to embed it so seamlessly that your user has no idea what is your embedded DSL and what is the host language. And we found that sometimes that works, but also we found that that can cause some frictions. So one example is like we had perfect seamless integration. This is kind of simple, but it just shows basically users do have curiosity sometimes about what is Mimi, what is Julia. Here is an example we haven't integrated necessarily into like the help functionality and documentation of Julia. So sometimes users don't know where to look, right? They're looking at Julia documentation. They should be looking at our package documentation. They're trying to use help in the REPL. They can't find it because it's not a Julia type. It's a Mimi custom type. So that can actually be quite confusing. And a second, maybe like nerdier example is that we tried to be fancy. So within our macros, we use syntax that looks very Julian. So we have lines that look a lot like a function call. It's not actually a function call. We write how this gets transformed. But we wanted it to look like Julia to make it simple. Unfortunately, we weren't quite clever enough. Someone was using an automatic formatter. It saw this middle line, and it put a semicolon behind the named keyword arguments. This is totally valid Julia, good practice. But we didn't put that in our macro because they get this crazy macro error that doesn't understand the expression. I don't know if you've seen expression errors. I don't even understand them, and I do code a lot. That's really confusing for a user. So there are these little things where if you try to make it seamless but you don't quite get there, you can actually get really confusing errors for your users. And I think I've kind of stated these design considerations. But yeah, so those are two findings that we had. And so we kind of recommend anticipating some confusion between the difference between a package or an EDSL and the host language, maybe pairing documentation to help people. So instead of rewriting Julia documentation, at least point them to the place where that might help. And then I think just like really strong attention to error messages. We catch as many as we can and then pass through with domain specific, but you cannot catch everything. They're gonna see host language errors, and just kind of thinking about that in design, I think is really important. And that's it. Thanks so much.
We have time for a quick question. You're closer.
Thanks. Yeah, that was really interesting, and I can see how that would really potentially help broaden the user base. I'm wondering if you see potential for collaboration between designers of different models like the ones we've talked about today, since I think most of us are in it for people to actually make regulation or make change based on it, not just to watch the world burn. So I'd be curious on your perspective on that type of collaboration.
Yeah. So happy to talk lots more about that after, but briefly, I think one thing that we've been lucky in is that has been basically working directly with policymakers as early as possible to understand what their needs are and what their goals are. And then I think the other thing that's just been important is to when we're designing this is to try, and we fail often, but we are both climate economists as well, and to really try to put our climate economist hat on instead of our computer scientist hat, because sometimes we get too fancy because we're having too much fun with Julia. But then when I watched users, I was like, they're not using any of the fancy stuff, right? Because they're just using the basic stuff that works. And so I think our priorities sometimes get mismatched depending on who we're focusing on as our user. If we are the user, we do different things than what they do, but happy to chat a lot about that.
Great. For the sake of time, I think we're moving on. So the next speaker is Oscar, who will talk about visualization and analysis of 3D lightning mapping array data.
Okay, I see my own screen. Okay, I gotta plug this somewhere. Where's the plug that you want to use? The HDMI is on this. Where is it? Oh, okay. There you go. Sorry. All right. Okay, yeah, this is my first JuliaCon, so thanks for having me here. And so I'm part of a lightning research group that uses lightning mapping array data. The lightning mapping array is basically a set of VHF receiver stations in a region that then can be used to map in 3 dimensions the lightning activity. So it's really a team effort of many, because you need quite some technical things to repair stations and to field them. So this is like the equipment. It's actually quite simple, and our stations are nowadays solar powered. And so what happens is these radio sources are mapped by GPS timing, and so you get points in a 3D space in a region of about 250 kilometers radius. And this is not the only LMA. There's about more than 15 light mapping arrays worldwide in operation, and they're typically used for for the science and for like nowcasting and warnings for severe weather. So we're looking for can lightning be used for predicting also other types of severe weather, like tornadoes or large hail. Also, this kind of instrument is used for validation of satellite instruments, like the GOES geostationary lighting mapper and the Meteosat 3rd generation lighting imager, which has just gone online this week. And I can already integrate them with my plots. And to the left here you see an old XLMA plot. So that's the original software that they gave with the LMA. But it tended to be very slow, and it was programmed in IDL. So there have been other efforts. Like in 2011, I made my own program in Scilab. I just like to get a hands-on with the data, and this at the bottom right is visualization. So you see like a typical map to the left, bottom left. The top figure is time altitude. So you see the individual lines are individual flashes, and then you have some side views. There's also another effort going on for Python, but I did notice that on their GitHub page, they noted that matplotlib, for example, is very slow, and they want to look for a solution which is faster. So I was in a chat with some colleagues from the US, and they are used to mostly the software on the left of this screen, and they, when I demonstrated the package, my new software, they noted like, oh, this actually plots instantly. So this is a very good thing of GL Mackie. So why Julia? Okay, so I wanted to develop further some ideas that I've presented at IUGG and various conferences in 2015, 2018. Had some ideas about leader speed, and I had some routines already developed, but it was very slow in Scilab, what I was using. Basically, Scilab is a sort of MATLAB, but free. I also wanted to integrate geostationary lighting imagers, because it's becoming very important right now. And so you need NetCDF reading, and they come in very large data volumes. So, okay, I intend to make this also a package for the Lightning community. Maybe, well, let's say within a year. I have to learn some things, and I have to round off this. So how does it look like actually? Let's visualize, because here I made a movie, because I don't risk I don't risk running it in the. I mean, it will work, but so here at the left you see, but that you can always say, and then it crashes, and then you spend the rest of the talk debugging. So here there are several things. So at the left you see the map. To the lower right you have a time distance plot. You see kind of the longer lighting flashes, the smaller. Now I selected the flash by clicking on it, and I can animate it. Like right now it's animating in time. Now I can select what I want to see on the color scale. So now it's plotting flash size. and it's still plotting by time in ordering. And now you can order, and I show leader speed. So this is one of the things that I programmed from scratch. So the leader speed is fitting a TLSEN robust estimator through the sources. And I use some trick to make it actually work quite fast. So let's look at some other examples. Yes, thank you. Okay, these are things that I do in terms of the data processing. So I make well, I'm used to C and IDL, and I just make as you see on top, LMA type. That's like a struct that you would have in C. And so I operate directly on this data, and so I read the native zipped ASCII files. I do well, a lot of gridding and noise filtering, and a lot of heavy lifting is done by dbscan from the clustering.jl package. This is really, really cool because I didn't have access to this before. So I chopped the data into flashes. So there's a certain spatial and temporal dimensions that govern these different types. Like you have sparkles at the cloud top that kind of persist, but in very narrow regions, and you can kind of highlight that with the dbscan. So this leader speed fitting that I just told you about, and from that you can determine the polarity and the charge structure of thunderstorms. So here is an example of these sparkles. So you see these little activity stuff at the overshooting cloud tops, and you can isolate them with the dbscan. And here's an example of the leader speed for a flash. So in 2013, I wrote a paper on this kind of diagram, which is a time versus distance diagram. Okay, time's up. So yeah, so you see the leader speed, and the leader speed basically indicates the polarity. So there's another tool that, well, I could talk further about, but I guess you just have to come to me and I will show you more if you want in real time. You can see planes in a lightning mapping array sometimes. Performance, Julia is 8 times faster than what I was using before. And I guess I should end with, where is it good? Yeah. Oh, we're here. Okay. If you want to see more like real-time data, but this is like a standard Python plot that is like, so you go to this website and you see real-time, if we have lightning, basically. So thank you very much.
Very quick question.
Yeah.
There we go.
I didn't know that lightning data was so good. Like it looks like you can almost like whatever you resolve is like I always thought like you could say like, oh, maybe there's somewhere lightning, but it's like
right.
You can really pin it down, right?
Yeah.
And so I was wondering, there was on the video that you showed, there was this like gap of like a little circle where nothing happened.
I didn't even mention that, but that's so this is a supercell, which is like the type that produces large hail, and it has a rotating updraft, and really you can see a lightning hole, which is, well, the first time that we could see that after we upgraded our LMA in our region.
How big is that? Like a few
the
kilometers?
The hole is well about 8 kilometers wide. This one. Yeah.
Cool. Very cool. Thanks.
Cool. Another round of applause, please.
Thank you.
Okay, so the next speaker is Simon, who will talk about supporting development of and operation of scatterometers.
Hi. So first, I just want to say thank you to our last speaker for mentioning MetOps 3rd generation and the new Lightning product we have out, because that's from HumanSat, the organization where I work. So it's really nice to hear that someone's interested in it. Yeah. So first, I'll just briefly introduce what HumanSat is. So we are an intergovernmental organization composed of different member states and funded by different member states in Europe. And our goal is to deliver, to establish, maintain, and exploit European systems of meteorological satellites. So we deliver a lot of Earth observation data near real time, so it can be used for weather forecasts and meteorological application. And then we also have a further objective of making the data available and useful for climate research and climate understanding. So very specific, I am in the remote sensing and products division, where I work with the scatterometer. So that's a very specific instrument, and I just want to introduce it a bit. Here we have on the screen, there's no mouse, but it has 3 arms, and each arm have two antennas. So we have 6 antennas in total, and these radars, they send microwave pulses down to the side, and then we get a reflection back. And we use these 3 antennas on each side to image 2 swatches, where we get like 3 observations for each point. So why is this interesting for weather? Simple diagram. When there's no wind, the ocean is pretty flat. Most of the energy is reflected away. When we got wind, we get some backscatter from the ocean. The more wind, the more backscatter, roughly. And using this, we are able to derive both wind speed and wind direction from these satellite measurements. We also have a soil moisture product, but I won't go into that because we have a limited amount of time here. So, how do we use Julia at EUMETSAT? I just made this quick slide to tell something about how we use it. So we mostly use it for internal things in my team. We use it to monitor the data. So we monitor the scientific part of the data. So we have the operations department, which monitors the voltage, is the instrument in the correct mode, has it the right temperature. We look at statistics of the data and make sure that everything is all right, and we're able to use Julia there. Visualization of the data. We do intercalibration. So maybe I should say the scatterometer instrument we have now are part of the MEDOP mission, and the first MEDOP satellite that flew for 15 years, but is out, and we have 2 satellites still flying in that program. But right now we are recalibrating the first 15 years of data and making sure it's really good intercalibrated and reprocessing it with the latest processor. We do it for regression testing, studies. We're preparing calibration and validation tools for the next generation. Where we don't use Julia right now is in the operational processing chain. So like the near real-time processing chain that all the weather centers depend on and that needs to run 24/7. First of all, it was set up quite before Julia because the satellite program has been going for quite a while. And then Julia is not a big thing in our organization. It's only like a small niche. So we only have a few programming languages which are allowed there. Just want to touch a bit on power to the user and what we're doing. I have this package called metanative.jl, and it's under development, and it's kind of the first Julia package at EUMETSAT. At least it will be publicly available. It's just a common data model for some of the MEDOP native binary formats. So it's a format that we use for some of the data from our low Earth orbiting satellite program. And we use this format quite a lot internally, and we also publish data in this format that are freely available and out there. Some data is only published in this format. So that's why I thought it would be nice for users to have a good Julia package to read it and use it, and a user-friendly package. It's also a way, again, to make something that I could use myself and my team can use, but also to give the ability to share the tooling that we use at EUMETSAT to work with our data with the users, so they could use some of the same tooling. Yeah, I aim to register this autumn, but I mean it's still quite new, so it only works for my sensor right now, ASCAT, which is the scatterometer. But I also get help for the hyperspectral infrared team. They have a sensor on the MEDUP satellite, and they are kind of the other team at EUMETSAT, which uses Julia. So it's really nice that they are also contributing. And I mean, we aim to not only cover our own sensors, but like just cover the whole satellite. So like all the data that we as EUMETSAT put out in the native binary format, we want the package to cover that. And also in all the format versions, because when you run a satellite program for over 20 years, then over 15 years, then sometimes the versions of the format changes a bit along the way. So that's also something we want to hide away. Yeah. And yeah, it's already on publicly available on GitLab, but it's not registered yet because it's not. I want to make it better before it's registered. Yeah. So thank you, and questions.
Are there any questions?
Yeah, nice. So how widely is Julia now distributed in EUMETSAT? Any chance that like the LI people have already some?
No, the LI people doesn't use it. Not as far as I know. So it's very much my team with the scatterometer, and then the hyperspectral team. And it's half the hyperspectral team that uses it. So it's for the higher level products they use it. So yeah, but I mean maybe in the future there will be more. But right now it's not a.
Right, and maybe a port for the data store access could be nice also. I can use command line anyway, but yeah, this could be.
Yeah. So I mean, but I'll have to talk with them about that. I looked a bit on it internally. I want to have like this out first, but then and we have the Python API, like to work with the API. But I mean, there could also be a Julia wrapper for it, but yeah, I haven't cleared that with anyone, so I don't know if I can make it. Yeah.
Thank you.
We still have time for more questions, if there are some. No more questions, so we move on. Thank you a lot. More applause, please. So the next speaker is Iga, who will be talking about how the Julia community reshapes computation in geosciences.
Working. Mm-hmm. Mm-hmm.
We've had some issues before with some Macs, so
Okay. All right. You can start around.
Oh, hello, everyone. Good to see so many familiar faces. Thank you for having us here. It's really good to make it to JuliaCon this year. So Iga Chesniak, she works at the Art Center. We work in the same team. I am João Pinello, Head of Data Science, Cloud Infrastructure and Development, mouthful, at the Art Center. We're still a very small team, so we have many hats. So I'm gonna... We lost the screen. Do you want to try this one? Yeah, good. So we're going to talk about a bit about the motivation behind the Art Center being involved in it with the Julia community. Do we still have image? and several things we have going on about power to the user, which is a topic here. So the Art Center, we are a relatively small organization, around 20 people. We are located in the center of the Atlantic in the Azores Islands. We are part of Portuguese and European national network of research. We are part of the United Nations Grid Environment Program, and we are part of the ESA Lab, which is labs for the European Space Agency. We have a data center located on the islands with the objective of creating synergies to work on main critical issues around the Atlantic, not just the region, but the whole Atlantic. So we have a direct receiving station. We track satellites and we get data in real time throughout the day. We have a data center to support that operation. And we get 300 gigabytes of data per day that we produce. We get the raw data and we produce products, and 300 gigabytes of those per day. So this is mostly raster data. So raster data are matrix parallel processing Julius. This is the logic behind our interest. The pipelines we have working at the moment for creating these products are from NASA DLR, and they are like 30 years old. They don't take advantage in any of the new hardware accelerators. So we want to change that. So we do in Julia scientific work. We build real-time data pipelines. Iga is going to show one. Capacity building initiatives in Julia. Develop production data-driven web applications. Repository for training based on the activities we do. And we're nurturing the Julia community for Earth observation by organizing annually the Julio, which is Julia for Earth observation. So in these events, we've had two. We're organizing the third one soon. Over 80 in-person participants, 46 speakers. We always limit the participants because we like to have hands-on sessions. Online, we have more participants covered over 50 sessions. So small outputs from Julio, getting all these people together. Tyler was born there. Tyler.js. The authors are most of them are here. Buyer Explorer is a new package that is written by a doctoral student of mine. I also introduced him to Julia. It's creating a package now. SAR processing started a little bit before the first Julio, but some authors are also here. So the main topics for the Julio events normally visualization, modeling, satellite-based data in general. Building packages, SAR data, we're working on SAR because on the islands there's a lot of cloud cover, parallel computing and scientific machine learning. So we have a very interesting capacity building project running at the moment, but we intend this to be a multi-year program. Harnessing space technological applications is sustainable urban development. This is in partnership with the United Nations Conference on Trade and Development. And it's a Julia-centered capacity building event aimed at some particular SDGs and with a bias for gender equality, which we have to look around the room. I mean, it's easy to see that it is a very biased environment, but we make the best to alter that. And on this note, I mean, these are series of workshops, but we aim to give support on a monthly basis so that whoever gets to be on the workshops, if they have a project they want to take forward, we support them on monthly meetings. So we emphasize here when we talk about this, the power to the user part, which for us is having the scientist contact with the users outside. This means having the full stack, and this is why we love Julia as well, because we can do everything on the full stack. We've done that in R in the past. I know, we've heard, but it's a great ecosystem. But of course, now we're transiting to Julia. So announcements, very quickly, Julia 25, 6th to 10th of January. Some of you have gotten the invitation already, some of you haven't, but doing that a few a day. And we're launching a Kaggle competition very soon, automatic identification of internal waves. This is just computer vision. Should be very simple exercise on the baseline, which I did in 2 hours in Python, yes. The baseline is 0.6 in terms of performance, so it should be fairly easy to go up, and there's a lot of room to grow there. So Iga is going to show her work now.
So we use Julia at the Air Center for Data-Driven Applications, and our first application fully implemented in Julia is a prototype of real-time vineyard monitoring dashboard. So the dashboard uses time series of the weather data gathered by the Internet of Things sensors that we have installed in the vineyards, and calculates the risks of the infection of downy mildew. It's a fungal disease that attacks wines, so that the winemakers can have a better insight on what's going on in their fields and can take more informed decisions based on the results. Thank you for listening. If you are interested in joining any of those initiatives, just let us know. We are always welcoming new people and want to have more people on board. And thanks.
Cool. Are there questions?
So I think the Vineyard application is a really interesting use of the data that you have. Do you have any real vineyards using the data? Are using your application? Is that sort of an expansion? And sort of what other groups or markets or things do you think would be fun to work with? Yeah.
This is our first application in Julia. It's totally in Julia, and it was a demo, and now we've been contracted to develop it further. Yeah, and it's expanding to other islands, and it's a service that could extend throughout the Atlantic region because it's our playground.
Are there any more questions?
I saw on one of the slides the call for the classification of internal waves.
Yeah.
How are internal waves important for the Azores?
It's not for the Azores, it's for the Atlantic in general.
Okay. Yeah.
And this is a really rare phenomenon. We have a new person working with us her PhD was focused on this work, and a lot of her time was compiling images, finding rare images with waves. And so Copernicus has a new service of imagettes, which are very kind of simplified SAR images. And you can get over 4,000 images in less than 2 gigabytes. And we compiled a lot we compiled nearly 5,000 images, 50% of them with waves. And so if we could have a service running running all images as they are produced and identifying positives and negatives will understand the phenomenon much better, and you get much better data about where they exist and try to understand the phenomenon further. I'm not an expert on that, but it will be useful to be able to automatically classify the images. So we get more positives, the universe of data to study is much higher, and we get to know the locations where these things occur and not occur.
Cool. Any more questions? Okay, well, thanks a lot. Another round of applause, please. And with this, actually, we end up the second block, and now we move on to the discussion.
Thank you everyone for coming. This was a fantastic mini symposium to run, and I'm really excited that it's the second year that JuliaCon has had a Earth Science mini symposium. And I want to say, like, comparing this year to last year, I think we had such a diverse array of topics, and it was really interesting to hear how people are coming together sort of from all over the range of climate and Earth issues. I do think that we ran a little bit over, but I think for the better in that we got more questions in and we got to really hear what everyone's talking about. So we might have a little bit of a short discussion because I want to encourage everyone also to go to the keynote, which starts at 5:10 which is in about 15 minutes by Dr. Catherine Hyatt, who's on the organizing committee. She does quantum chemistry at AWS and is super cool, so totally encourage you to go to that in the closing. And I guess a logistical note, we booked a dinner for the speakers, but we may have extra space. We're going to go at 7 p.m., but maybe meet downstairs at 6:50 if you're interested. And we'd love to have as many of you as we can logistically manage with the restaurant not getting mad at us.
Yeah, exactly. So do obviously please show up if you have interest. We just booked for 16 because we didn't know how many there would be. And I guess the others might just need to sit at another table. Also, I don't know exactly how big the restaurant is. We haven't been there. But in case you miss us, it's the Gazana Eritrean restaurant. That should be just a 5-minute walk. I think if you came from there, it's kind of also that way, but not quite to the city center yet. I think if you just Google for Eritrean restaurant, you will definitely find it. There should be only one in the 5-minute walking distance. Yeah.
Yeah, but we would love to, even though we'll have a bit of a maybe short discussion here, maybe no discussion here, but we would love to continue this and build some collaborations. And it was amazing to have such a large audience, including speakers and in addition to speakers here today. Yeah, should we just close? Or does anyone have any concluding comments or things that they would like to comment on from this session? Please do.
So yeah, actually when you showed a bit the documentation of speedy weather, and I guess that also aligns with Oceananigans, it's not really in line with typical documentation, which just includes an example and how to deal with the software, because you have a textbook, as you said, with equations and describing the physics. I mean, yeah. But so yeah, what are the thoughts generally on that? Because I feel I buy the idea. I think it's a good thing, but it's maybe a bit unusual compared to other parts of the community that don't necessarily describe the details of the equations that are used. So what should we prefer? Documentation that's updated very regularly with the latest physics, papers that describe this, a mix of both. Do you have any takes on that?
Yeah, I find that a very interesting question because obviously, if we develop packages, there's a wide range of different documentation, as you said, that we can provide. One is obviously the use cases. Sometimes you also might just have a list of all the doc strings, and just basically so that you can easily search the documentation and find okay, this is the expected arguments for this function, this kind of stuff. I feel that in model development, what we often end up with is that you pick some ideas from different places, and so there's not this one paper that describes your method exactly, and you take exactly that one over. Sometimes you take shortcuts, sometimes you feel oh, I take this piece from here, this piece from there. And so at least in my case, in our case, that was really the case where we said okay, somehow we have to document the puzzle pieces that every like model development puts together. And so basically you're then ending up in a situation where you say like, okay, I guess we have to write down the equations and say which shortcuts are we taking, which pieces come from where. There's usually then kind of like a, let's say like a, this is the equation we're solving, this is how we're solving it. For more details, find it here. I think this is in general like good practice. Unfortunately means also it's a good amount of work that comes on top of it. So it literally took me like a couple of months to basically write that down, all of that. Some of that is somehow copied. It's a good question. I find this is also for the wider community really a question of like what is the, because I mean there's a lot of stuff where suddenly people like start reusing packages from other people. Is there like, are there like typical gaps in documentation that we need? How can you basically, I don't know, do you, if you kind of feel like, oh, this is a good package, but I don't really know how to use it, how to interface it, do you basically say like a request to like more documentation on this? Does that put too much burden on the developer? Because obviously if someone, no, I thought you had an idea and wanted to say something, wanted to say an outcome. Yeah, I think it's definitely a good discussion point. It's maybe if someone has another point on that, please raise your hand. But otherwise, I think it is also something that's really good to discuss. For example, over dinner, of like, hey, like, how do we make sure that all our stuff is interoperable?
We definitely don't go to the extent you did with the equations, but we often put math latex in the doc just to be like, so it's not just the code. If it's coming, we'll put the paper it's from and the math latex just to round out explaining what we're doing. Yeah.
Felix, did you want to?
Yeah, just about the gaps in the documentation. When putting packages together, we started a Julia Geo tutorials repository, and there's a tutorials wishlist issue. So if you find something that is missing, or where you find there's a gap, that basically you have two packages that kind of work together, but it would be good to write this down, put this there. So at least we have a list of stuff that we want to work on.
Yeah, that's a very good point. Yeah, like it resonates with me deeply, this documentation thing. I do like the idea that, you know, essentially documentations become like textbooks. For me, very important bit of the documentation is having like examples that in the code, make sure the code is really updated. So when you have like examples that are iterated as soon as you commit something, then you are ensuring that, you know, what you get is what you will get with, you know, that version of the package. I think that like changed my life, because I don't know if you try to go to any other model, and, you know, I don't know, I have struggled a lot with that. And then you know, you had to go and literally knock the door on some developer to figure it out. But in the other aspect, like what Milan was saying, like, you know, when you get, instead of getting a request like, oh, can you put more documentation here and there, so then putting all the pressure on one or two developers, it's much easier if, like, you know, we can have some way of interacting, figuring it out a little bit, and then, oh, here's a tutorial I made, or like I'll try to help make a tutorial, and then, you know, we work together. That's like much more. When we get that, it's like, oh, all right, okay, I know I'll put some effort here. I'll, you know, like, you know, it's like more of an investment, and then we'll have a new contributor or something. That's much better, instead of like asking, because then we have like 100 things to do. Anyway.
I think we could do one more quick comment, and then, yeah, out of respect for the keynote, we'll cut it and continue at dinner.
Yeah, very quickly, I think I totally agree with that. Like, my experience sometimes with some packages, like, I try to use them, I break my head trying to make them work, but once I understand, it's just like, oh, I got what I wanted, I move on. And sometimes I was like more, okay, like, can I at least like empty my brain into the documentation, even if it's not super structured, but at least I do like a very tiny contribution, at least the next person in line doesn't go through the same pain. And sometimes I feel like PRs on documentation are like the lowest hanging fruit for like contributing to packages. So I think it's kind of like something that I thought it was nice.
Amazing. Then. Great. Okay.
Yeah, I can say I went to that. It was pretty good. You can check out the materials.
Yeah. Okay. Great. Really last point, or otherwise we just cut it short here. Sure.
Just a quick one.
Yes.
One thing. So as a package developer, I work on GeoMarchy, right? One thing is that I'll often never hear about use cases that do work. I only hear about use cases that don't work until the use cases that do work break. So if you guys can I don't know what the best channel for this is, but maybe post examples of use cases that do work, and then we can sort of test those, make sure they're stable, and so on.
No, very, very good point. Great. So then we're coming to the end of this mini workshop. I feel like if anyone is bugging me and like Skylar did last year, we can probably definitely have one of those again next year at JuliaCon. So if the whole community is excited about this, we can have something similar. I think that's very exciting. Maybe some of you will be at Julia EO on the ASOS in January. Otherwise, we'll just close it here. I'm very much looking forward to the dinner. I think you have all the details. Otherwise, bother us again. And thanks so much for coming. Thanks so much for contributing your talks. I'm really looking forward to the dinner, but also all the progress you will make in the next year, and then happy to see all the results in 2025. Thank you. Of course.
Dinner thing that you said?
So we booked 16 places at an Eritrean restaurant. We kind of said hopefully as many speakers would come around as possible. Everyone else is also happy to come along. We don't know exactly how much space they have. Otherwise, we do it in the Greek restaurant. We just extend or ask them whether they can have another table. We would start at 7, just meet downstairs with the teacher.
Right, but where is the place? Because I may just come later.
Yeah, Gizana Eritrean restaurant. It's an Eritrean restaurant that's like a 5-minute walk from here.
I will just write it down quickly. Gizana.
It's a dinner, right? Where is it?
Gizana Eritrean restaurant.
Eritrean restaurant. I heard train restaurants. That's like,
No,
all right, train
Eritrean,
restaurant.
sorry.
Yeah, it's probably if I Google train restaurant, I'll find it. Yeah, Eritrean restaurant. All right, great.
I think it's the only one.
Yeah, I mean, I'm sure. Eritrean restaurant. All right, okay. Yeah, 7, you said? 7?
Yeah, so meet down here at where the teachers are,
yeah.
10 to 7, 6:50, so that people can go to the keynote and then have some concluding discussions at the end. I find the whole community is still basically missing shenanigans is on a good way to get there, but missing killer applications. Killer applications. What do you mean killer applications usually what customer knows for Game Boy.
Yeah.
So the kind of the applications that people are so excited about that they buy into the technology.
You mean for documentation. I see.
Yeah. So for the 3D cinema thing, it was Avatar, right? So these kind of things are
I don't know. Maybe I think people are sold that this documentation helps. It's just they don't put the effort when they're doing, I'll make a PR for this new feature. They don't even do tests sometimes. So they, let alone writing something. Yeah, I don't know if it's like that. I think people are convinced, my opinion. It's just lazy. But then when you do it, then you get 100 more users, and then
yeah, for all the questions, can I do this? You're like, yes, it's in the documentation.
Yeah.
Yes, 5 lines of code.
all right, keynote.
Yeah, exactly.
data?